All right, good morning. All right, everybody. I guess we'll go ahead and get started. This is the ICDD database and JADE workshop. I'm Tom Blanton and joined by Anja Dosen. So we're going to have a combination. I'll start with database, the PDF5 database. I think we'll run it at or near lunchtime. Lunch is outside. And then Anja will start with the JADE and particularly emphasizing Clay's analysis. Just a couple of comments. I guess everyone's had opportunity, wireless access. So what you're doing is you're accessing the database in JADE on a remote desktop server based out of our server office in California. Okay. You will have access to it for the rest of the month. Okay, I think right at the end of the month. So beyond here, you'll have a chance to work with it, try it out a little bit. Anja and I will also be here this week during the meeting in one of the expo exhibit areas. So certainly you can stop by, ask questions while we're here. All right, so let's get started. I'm going to just go through a couple of background slides, and then we'll start the actual hands-on activity with the database. So it is the ICDD workshop, International Center for Diffraction Data. Just a couple sort of historical aspects here when we think about X-rays. The early years, of course, the beginning was Röntgen, credited with the discovery of X-rays. This is his first published radiograph. It's a picture of his wife's hand. You can recognize it by the ring that's on her finger. Sort of the joke is that at the time they didn't really know what they were working with. Röntgen knew he wasn't going to put his hand in the beam, so he had his wife put her hand there and take a picture of it. Okay, so at the time they were referring to these as shadow graphs. They really didn't have radiography. Lowy, 1912, along with his graduate students, Knipping and Friedrich, discovered X-ray diffraction. This was the first diffraction pattern, which doesn't look very good. It's a copper sulfate pentahydrate crystal. And they actually had the film 90 degrees to the X-ray beam. They didn't quite understand what diffraction was going to be. Soon they figured it out, and then they had it more in a transmission mode with the crystal, and they got a very nice Lowy pattern. But this was the start of diffraction. Moseley, 1913, is credited with the discovery of what we call X-ray fluorescence, where he was able to observe on photographic plates emission lines when different elements were irradiated. And it's from here they came up with the concept of characteristic radiation in X-ray fluorescence. Now, the Braggs, father and son, credited really with doing the first crystal structures from X-ray diffraction. And this was a diffractometer of the day around 1913. You put a single crystal in this location here. Someone would reach down and rotate the crystal while it was being irradiated. You had a gas field detector here. And as you rotated the crystal on a specific face, you would see your diffraction lines. In this case, it's a platinum anode X-ray tube, and they were seeing the L alpha, L beta, and L gamma lines. So they're looking at a 100 face and a 111 face. And it's from this information they were able to deduce some of the first basic crystal structures. Now, up till about 1916, the belief was that if you took a crystal and crushed it, you destroyed the crystallinity. It was Scher, Divine Scher in Europe, and Hull in the US were simultaneously working on the concept of powder diffraction. What they were able to deduce was that you didn't necessarily destroy the crystallinity, you just made smaller crystallites. And if you had enough of the crystallites in a random distribution, you would get these diffraction rings comprised of spots from all of the different diffraction crystallites. We refer to these as Debye rings. DeBuy and Share published their paper first, and so we refer to it as the DeBuy Share technique. What Hull did, however, expanding this, was he showed that if I took two different phases, sodium fluoride, sodium hydrogen fluoride, and I mixed them together, I didn't get a new diffraction pattern. I got an overlap of the two patterns, and so he was the first to show phase identification using powder XRD. It was turned into an industrial process by the Dow Chemical Company. This is a picture from 1934. Remember the days they were using film as your detector. They had set up an apparatus with an X-ray source. They had 12 cameras around the source, two capillaries of powder in each of these. So at any time, they could be looking at 24 different samples, and they would get a series of these diffraction film strips, and they'd use these film strips to do some kind of phase identification. In 1938, they published the seminal paper on analysis by X-ray diffraction. This is the original Hanawalt manual. What they did was they would record what they thought was the chemical they were working with and the despacing of the three most intense diffraction lines. Okay? And they used perturbation of these lines to help do the identification of materials. In 1941, they connected with ASTM, American Society of Testing Materials, and came up with the first powder diffraction file entries. And these were on index cards, US size 3" by 5". And they would record the despacings, relative intensities, and at that time, the most intense peak had a value of 1. Okay? These were handwritten. Whoever wrote up the card put their initial here in the corner. This is H for Don Hanawalt, the person who originated the powder diffraction file. Now, one of the questions I always like to ask is, why did they put D space instead of 2 thetas? They didn't know what radiation someone was working with. Different people had different anodes for their X-ray tubes, but the D spacing was consistent for the material. Now, if they knew the unit cell, it would be recorded. If they didn't know the unit cell, it was just a list of D spacing. So this was the start of the powder diffraction file. Today, the powder diffraction file now, of course, is all digital. This is what we're going to be working with today. Been around since 1941, so the name went as associated with ASTM. Became independent organization in 1969, the Joint Committee on Powder Diffraction Standards, JCPDS. Some people will still use that name today, but officially we're ICDD, the International Center for Diffraction Data. And I thought for a little fun here, I had the opportunity to see the Book of Kells a couple of days ago, okay? And thought it was interesting here. So, hey, doesn't that look familiar there? And if you highlight that area, so we say we've been around 84 years. Well, doesn't that look like ICDD right there? We've been around 800 years. You know? So, anyway. But anyway, if you haven't had the opportunity to see the Book of Kells, I certainly recommend it. It is a really nice feature to see across the way. Okay, so what is the PDF5 Plus database? It's comprised of data from ICDD that we've collected over these 85 to 84 plus years. We have data from the FIS ICSD database in there. We have data from NIST. We have the Linus Pauling file, and we have data from the Cambridge Structure Database. Now, we don't have all CSD entries. We have the entries that are in there for the purpose of doing phase identification and quantitative analysis. You want to do molecular modeling, you would want the full CSD. But the PDF5 Plus is the full database, most comprehensive powder diffraction file database out there. So on our login that we've done here, there are a couple icons. One is for PDF5 Plus. The other is for JADE. we're going to be doing JADE after lunch. So this morning, we're going to work with PDF 5 Plus. If you haven't done so, go ahead and click on that icon and you should be at a page that looks something like this. And the opening page shows a number of the search data mining parameters available on PDF 5 Plus. And the most popular is the periodic table search. So that is the default that shows up. But just a couple of the items here. Here are the different databases that are located into the database. There are over 1 million entries in PDF 5 Plus. And if you happen to be looking at inorganic materials and you're not interested in the CSD organic materials, you can click on inorganic emphasis. And so it will not use the CSD data, though you can always go back to it if you want to. For our purposes today, that's what we're going to work on is the inorganic emphasis. We have the different databases. You can look for entries, which ones have atomic coordinates. We do have raw data in the database, and I'll talk about ambient, non-ambient data. There's a category here called status, primary, alternate, deleted. So what does that mean? There are sometimes more than one entry for a certain phase. Like if you look up quartz in the database, you'd see there's several quartz patterns. And the reason for that is depending upon where the sample originated from. Is there some kind of doping in it there? What kind of instrument was used for? But we do review all the data and we will mark those few patterns that are the best, the primary. So if you only want to search a few patterns, you could certainly remove alternate. But you also see this category deleted and it's unchecked, which means by default, it's not used. But when an entry is either replaced by better data or an entry is found to be incorrect, database management, you do not remove that entry, you simply mark it deleted. If you wanted to go back and look at it, you could, but it will not show up in a default search. Classic example of why some of these show up. Somebody maybe has a patent litigation case and they were referring to a pattern in the database that was an older pattern. So it's not removed. You simply have to go in and manually look for it, but it's not going to show up in a typical search. And then we have a number of search categories, the periodic table. So we're going to go through these today. I want to emphasize one point here about the quality marks. The powder diffraction file, every entry has gone through an editorial review. An editorial review looks at the data, and particularly when unit cell is known, delta 2 thetas, errors in the data, any issues or problems. And in this step, a lot of entries do not get into the database because they don't meet minimum quality standards. Now you'll notice that we sort of put a sort of like a traffic light situation. Green meaning go, this is the best. Yellow, at least in the United States, for a lot of people in the traffic world, it means speed up, hurry before you get through the red light. But the idea is it's okay, it's good data, but a little bit of caution. And we'll have a comment why we've made a mark on this one. Red means be careful, it's a little bit low quality data. Why would you put low quality data in the database? Well, sometimes it's the only entry that's ever been reported. Something in the literature, maybe some old camera data. Maybe we find some delta errors in it, so we'll mark that as a note to say, be careful, okay? And then we do have a few hypothetical structures when we find that would be useful, but they're not part of the automatic search. This would be something you would have to say, let me search through hypothetical structures. Let me give you an example why quality matters. This is a paper published, and the paper said that this was a pattern of sodium alginate. Now, sodium alginate is a biopolymer salt. And two things stood out when we looked at this pattern. One, these sharp peaks here. Biopolymers tend not to have really sharp peaks. And the second thing is we have a study at ICDD going on looking at polymeric materials. And we had a reference pattern for sodium alginate, and this has none of those sharp peaks. Now you'll see that there's some general broad bands here consistent with what we see here. But what's going on that these sharp peaks are there, which is typical of some large crystallite material. It turns out that they had washed the sample with some dilute sulfuric acid. Sulfuric acid leached out sodium, and the sodium precipitated as sodium sulfate. So these are the things that we check before putting the patterns in the database. So other databases might say this is the pattern for sodium alginate. The answer is no, it's not. So this is sometimes also just in general reading the literature. Be careful when someone makes a claim this is the diffraction pattern, particularly the diffraction pattern is in the paper and it's, little thing, 2 centimeters square, and they're trying to tell you that they've identified 15 different phases in the sample. Be a little bit careful and cautious. Okay? All right. So let's talk about getting started here. So the first thing is we're going to just open up a specific PDF entry. Now, when we do this, this is a case where you know something about the entry you're interested in. So you'll see here on your example of the search menu, at the upper left is a thing called PDF cards. Now keep in mind, it's no longer really a card anymore, but this is the tradition of what they are. It's really a PDF entry, okay? And if we click on that, a little pop-up is going to show up here that we can enter in a number. And the number we're going to look at starts with 00. From the beginning, we talked about our different databases. 00 is data that's derived from ICDD, 01 FIS, 02 CSD, etc. Okay. 74 tells us it's the set number, 74 set. And then 1030 is the actual entry number itself. So let's go ahead and when we do this, we're going to do something like this and an entry is going to show up. So let's go ahead and do this together here. So should have a menu periodic table like this. In the upper left where it says PDF cards, if you click on that, please. And let's type in our entry number 00. Okay. 074. I know it's in front of me here. And then I want 1030. Okay. Yep.
If anyone has a problem or a question, just call my name, Anja, or hey, and I'll come and help you out. Okay?
All right. Okay, and when you're ready, click on Open PDF Card. And you should get something that looks like this. Whoop. Okay. Everyone's okay with this? All right. Okay, so what does this tell you? So this particular entry happens to be for sodalite, okay, sort of a cage-like structured mineral, okay. We put a note here whether it's if it's natural, it's fine. If it's synthetic, then SYN is listed after, okay. We have the IMA symbol if it's known, okay. Some chemistry information, and then some data along here. Now I mentioned the Hanawalt method. And in the Hanawalt method itself, you relied on the first 3 most intense peaks for helping with your phase ID. So one of the things you'll see now in this particular entry here is it has a list of the D spacings, has a list of relative intensities, in this case, relative to 1,000. Okay. And then the unit cell must be known because the Miller indice HKLs are reported. You'll notice also in this one, though, that the 2 thetas are reported. Because it's a digital database, we can do that. And in fact, we have the option to change the wavelength we're working with. Typically, the default is copper K alpha 1. But if you click on the drop down, you'll see that we have a list of the more common laboratory-based sources, plus something called user-defined. So if you happen to go, say, to the synchrotron, you could click on user-defined and put in the synchrotron wavelength you're working with. Let's call it 1, 2, 3, 4, 5, 0.1, 2, 3, 4, whatever you happen to be working with. And what has happened now is all of my 2 thetas have been recalculated because it's now much lower angle than it was when it was copper radiation. So the advantage here is just for visual effect, you can see no matter what radiation you're working. Okay. All right, I'm going to go back to the copper K alpha 1. Okay. All right, now I mentioned about seeing the 3 most intense diffraction lines or diffraction peaks. Those will be highlighted in extra dark text. So you have one here, one here. If I scroll down a little bit, I'll see the 3rd line. Those are the 3 most intense peaks observed for this particular material. Okay. But in addition, you have what we call a simulated pattern. What's the simulated pattern? All entries in the database have the D spacings, okay, and a simulated profile's been put along it, so you get a general idea of what it looks like. So come up here to the icon that says simulated profile. Let's click on that. And you should see something that looks kind of like this. This is just a simulated pattern, and we can play with this a little bit. You see there's a blue arrow here to the right. If you were to click on that, right now, the pseudo void is the profile function. It's the default that's there. If you click on its drop-down arrow, you'll see that there are a couple other functions of what you want the profile shape to look at. But let's explore this one called crystallite size. Click on crystallite size, please. Okay, is everyone good with this? Okay. Now, the default showing up here is a crystallite diameter of 25 angstroms, and it's showing what happens to your diffraction pattern when the crystallite size gets smaller. Your peaks get broader. They're broader because you have fewer lattice planes for constructive, destructive interference. And you just get more scatter coming off. And you can adjust the crystallite size here to some other size, and you'll see how the peak starts to narrow up a little bit. Now, this is not a felt refinement. This is just a modeling to say what the nominal size. But it's a nice little feature just to get an idea of what painting pattern. Okay. Now, in addition to that, there's something called bird orientation. Takes the March-Delage function and says, assume that your material is either platy or needle-like. What would that do to the diffraction pattern for preferred orientation? So if I say that I'm looking at preferred orientation and I take my scroll bar and I roll it towards platy, I see how the peak intensities change. And if I want to know what lattice plane changed, I can always take my cursor, put it along the strip of markers there, and see. Now you notice that when I'm my cursor's on this line here, it says that's the 200 peak. I'm looking at preferred orientation for 001. Well, this is cubic. So now suppose I said I've got more needle-like orientation. I'll take my scroll bar. I can either scroll it along, or I can put a number in here for my March-Delage function. And you'll see again how it changes the relative intensity of the peaks. So the idea here again is it's not a refill refinement, but it is an idea of how your pattern's going to change. Something, for example, you want to see in platy clay. Yes. Basically, that's the March Delage value. So the range is based on when March Delage, when they came up with their formulation, they basically said they came up with a mathematical function that said it goes from 0.2 to 1 to 5. 1 means random orientation. 0.2 meant platy orientation. 5 meant needle-like. It's almost like an orientation distribution function. Okay. All right. So let's close this for a moment. X out. You'll see another option here called raw diffraction data. If the raw data has been collected and put into the powder diffraction file, that icon will highlight. If it has not been reported or sent to us, it'll be gray. So just click on raw diffraction data. And this is the actual pattern the individual collected. Yes.
Yeah, this before we move to the other part and from these before the simulated profile, we switch the source of the radiation, the simulated profile, let's work that up to this.
Yes.
Okay.
Yeah. So if I change the radiation, it'll shift all the peaks to the correct angle. Okay. This is the raw data that the individual submitted. Now, it may not look a whole lot different than the simulated pattern, which means the crystallinity was pretty good for this sample. Okay. But we're going to show you in a couple minutes cases where having the raw data is very beneficial because not all diffraction profiles are nice, like this one here. Clays, for example. Okay.
So this raw data, is that the reason in the difference that you see here, the most intensity is like 2.5 times the biggest intensity that is reported in the table that we report.
Right. So when we're looking at the actual reported data, I'm going to close this. The data that are reported here, if it's an experimental pattern, like the OO data from ICDD, this is the actual collected data that someone's reported. Now, when you get into the FIS database data, the O1, the CSD, LPF data, O4, etc., those are all calculated from crystal structures. So you won't have the raw data, it will just be a calculated pattern. So then when it's reporting the intensities, and the D space, it's based on the unit cell and the atomic arrangement within the unit cell. Okay. Good question. All right. Okay, a couple other things just to take a look at, just for informational purposes. You have this now, it may be a little slow because of the going to California and back, but you can click on 3D structure. And if you click on that, you'll see this sort of a cage-like material, and you can either spin it around or if you want to have it automatically spin, rotate for you type of thing. You can even record this spinning and insert it into a PowerPoint presentation or something. Okay. All right. A couple of the other extra features. You can get these simulated. So if we know the structured material, we can look at the simulated selected area electron diffraction pattern or the backscatter pattern. There's two options. First one, if I just click on the sort of the little black icon for SAED, you'll get a simulated type spot pattern. If you move your cursor over the spots, it'll tell you the particular HKL the spot represents. I don't have this particular raw data for this one, but you'll see up in the upper right-hand corner file. If you were to click on that, you could import an electron diffraction pattern and overlay it with your material here. You can change either the camera constant or camera length to your voltage, etc. So you can make adjustments for the parameters you're using in your particular setup. Okay, so this is one simulated way. Let's see if our speed is high enough today. On the SAED, there's a little drop down arrow. I'm going to click on that, and there's something called the SAED extension. Let's give that a shot, see if we have enough bandwidth today or not. Now here, it's a little bit additional information you can do for the SAED, where you'll get a simulated pattern on the left. You'll get the stereographic projection on the right. If you look up here where there's sort of a little sort of 4 dots here, sort of in a cross X shape there. If you clicked on that, it'll put the structure in front of you. And if you rotate the structure, you can see how it changes your SAED pattern. What's that?
Yeah, there's a connected arrow.
Okay, so it could be the speed's a little slow.
It says because so name on.
Yeah, I know, it looks like this is not enabled for yet.
Well, I'm on the same, well, you know what, I'm on this,
You did?
Yeah.
all right.
Maybe that's how much bandwidth we had for 2 people.
Yeah, I mean, maybe someone else. Yeah. I think that.
Okay, I mean, I know I'm on the RDS as well too. I guess, I don't know what they have it here in Ireland, but in the US we have lottery tickets, and if you're lucky, maybe we should buy lottery tickets, because yeah, so it could be something with the connectivity. So I'll show you what we have here. And if you wanted to, you could show a little picture here where you can change the, say I want specifically 110 alignment. And I can say, okay, I'll realign the crystal as well as my stereographic projection. Okay. What I would guess is that when you're back at your site and you're on your regular internet, this should proceed through. Okay. All right. Okay, I'm going to close that. EBSD, backscatter pattern, same kind of thing. You can get the standard projection here. Again, changing your instrument conditions for your backscatter pattern. You can also, again, the same kind of thing, the EBSD extension. And you would see something like this. And again, you can put the crystal up there, orient it around, so you can see your EBSD pattern as well. Okay. All right, just a couple other things to show you what we can do on an entry. There's also something called ring pattern. If you happen to be using a 2D detector, you can essentially simulate what the pattern would look like. And again, you can change your radiation. You can also change your detector to sample distance, whatever it happens to be for your particular setup there. You can even play with the crystallite size here under the rings so that you can make them more broad if the crystallite size is small or large. And sometimes people like to say, let me emphasize the low intensity, so I can do square root or log of the intensity as well. And of course, for entertainment purposes, you can make the rings different colors. Okay. All right. All right, so to give you some ideas of things you could do. A couple other things here. There is a bonds extension. I'll just show you that one as well. And here, if you want to look into some of the distribution of bond lengths for particular components, This is a sodium, aluminum, oxygen, silicon chloride. Right now it's showing the distribution of bond lengths of sodium and chlorine for the database as well as for this particular structure. But if you said, let's show me the distribution of aluminum oxygen bonds, for example, I see a distribution of those. So for people who are a bit more into maybe pair distribution functions and they're looking at bond distributions, this can be used for that as well. Okay. Now, not every entry has all of the features. There are some entries where someone just collected some experimental data. We don't have the crystal structure. Then there's a lot of things you can't determine if you don't have the crystal structure. Okay. Okay, one last thing I want to show is that there is a thing called cross references. And on the cross references, you can look for any of the 04 entries. These are the LPF from crystal structures. I'm going to click on the one here that says primary. Does everyone see that? Primary 04008. If I click on that, that particular entry has now opened up. 040082098. Again, it's also sodalite. And on this particular case, you'll notice now it also includes the option of showing neutron diffraction simulations. I'm going to click on that. I can either be working with constant wavelength. It just by default puts a copper number in there, but if you happen to have a neutron wavelength of 1, it'll calculate the pattern. Okay. And also it will simulate the time of flight pattern. So if you happen to be neutron studies, now the thing with the neutron studies, we also have the option if you have used some kind of isotope change in the material, you can change the isotope of the elements that are present, and that can dramatically affect intensities with them. Okay. Okay, so that's kind of a broad view, though, to understand, though, there's a lot of things you can do. I'm going to close these. A lot of things you can do with a PDF entry. Okay. Good so far? Okay, all right. Now, what happens, this is the case of I knew the entry I was interested in. I don't know the entry I'm interested in, but I know the kind of material I want to look up. So how do we do that? Okay. So for our next example, what we're going to do is we're going to do some data mining searches. Okay. Okay. PowerPoint for 1 second. So I mentioned raw data in the powder diffraction file. When you have nice crystal material, well-defined peaks, simulated pattern and the raw pattern are not too dissimilar. Maybe a little asymmetry at low angle due to axial divergence, but in general looks okay. Clays, on the other hand, just do different things, okay? Depending on the clay, has it been treated? Anja's going to get into clay work this afternoon. So we have been putting raw data patterns in the database, and this is where it really helps. This is a halloysite type clay, and in particular, the asymmetry in the peaks. The traditional D-space intensity that goes into the powder diffraction file won't describe this profile. And so we actually put the raw data in there, and an individual can actually open up that raw data, import their pattern, and compare them for the identification. Okay. Beyond clays, other materials we put it in there for, there's a lot of polymers that we've been adding, because polymers also tend to have broad diffuse bands. It's not well sharp defined peaks. This happens to be Nafion polymer, which is used in fuel cells. At low angle, has some ionomer component. At wide angle, it's amorphous type polymer. 3D spacings won't explain this pattern, so that's why we put the profile in. We put patterns for nanomaterials in there to help understand why the peaks are broad. So this is zinc sulfide, but in looking at the zinc sulfide here, you have a peak here. There's actually two peaks right here. And again, helping people understand why my profiles are broad when it's nanomaterial. And we even have a diffraction pattern for water in the database. Water does have scatter. It's amorphous, but it does have a scatter pattern, so it's there for reference. Okay, let's go back to the search form. And again, there are many options of things that you can do here. The most popular is the periodic table search. So let's do an example of that now. Okay, so let's go to the periodic table. Okay. Oh, excuse me, I'm sorry. There is one thing I wanted to show you. In oops. And I'm showing you the database that's actually installed on my computer. Online, the remote desktop server, there's a feature that is not available. It's called export and print. If you have the database at your site on your computer, you can export all the entries as a CIF file. Brooker specifically asked us to allow you to export it for Topaz as STR, or you can do XML file. In addition, you can also print or get a PDF of it. Why did we take it off of the remote desktop server? We had a course in a country that the individuals decided, oh, that means we can try to download the whole database. And that's not what the intent is. So we did remove that. Now, you're a student, you're at a university, you need a couple of entries to do some match to finish up your work. You can write ICDD, we'll send you a couple of entries. You need 100 entries, we use by database. Okay, but if someone needs help, we provide an entry to help someone with some identification. Okay. All right. Okay, let's do a periodic table search. Now I'm going to go through a few different options here. I want to do a search for iron, cobalt, and oxygen. Now let's look at what's happening when we click on those elements. I've clicked on 3 elements. You'll see they're highlighted now. And here along the bottom, they show up in my list of what I'm searching. The default, remember, I excluded, deleted, and hypothetical patterns already at the beginning. Other thing you'll notice that now that the periodic table is active, that tab now has turned red. It's to help you know which things are active, okay? And then you have Boolean search, and or only just. Okay, so we're going to do a search of iron and cobalt and oxygen. Now, right away, we get a little hint that in the database, there are 2,856 entries that meet that criteria. And make sure, just for all of us are on the same page here, up at the top, where you have the option of all data, inorganic, emphasized, organic. Let's do the inorganic emphasized. Now, there are some organics in there from the ICDD data, but we're not going to be looking at the CSV data. And when you click on inorganic emphasized, the CSD now is grayed out. We're not searching the Cambridge structured data. All right, so let's click when we're ready. In the bottom left-hand corner is a little search icon. Let's click on that. Oh, sorry. Actually, the answer is I'm Tom Blanton. Okay. All right, sorry about that. All right, so let's click on the search icon in the bottom left corner. And I get 2,856 out of 512,873 entries. Okay. Now, what did I say I wanted to look for? Iron, cobalt, oxygen. And I use the AND Boolean operator. So I look here, yeah, that looks good. Okay. Wait a minute. I didn't say barium. Why is barium showing up? With the Boolean operators using AND, it means it must have those three elements, but it doesn't exclude other elements. It just has to have those three. Okay, so what I really want, if I want to be exclusive, I need a different Boolean operator. Okay, so I'm going to close this search, the little red X here at the top. And instead, I'm going to click on only. Okay, and when I do that, notice now my hits go down to 169. All right. Let's click on our search icon in the bottom left. And now as I look at the results, different combinations of the amount of iron and cobalt, but indeed I have only those elements. Okay. Now, what does this mean when I have this search result? I'm going to just open this up a second so we can see in a second here. Now, what things are included here? Well, the PDF entry number, the quality mark, the chemical formula, the name, the three most intense diffraction lines, the diffraction peaks, and the crystal system. Okay. Now, as I'm looking at this, suppose that I want to see a different order, that instead of numerical order of the database entry, I want to see the quality mark. So if I click on the QM column, click on that header there. And what it does now is it will order these all as the highest quality, star quality mark. If I scroll down a bit, eventually I get to the sort of mid spot. And if I continue down further, eventually I get to some lower quality data. So I can see the highest quality, good quality, low quality. If I click on QM again, what will happen is I will reverse that order. I'll scroll back up to the top. Now I have the low quality, mid quality, high quality. So it's just a way to reorder these. And at any time you want to get back to where you were to start out with, click on PDF number and it'll put it back in numerical way. Okay, let's click on the column SYS for crystal system. And you'll see here in this particular case, I've put the, because I clicked on it, I've got lower symmetry, orthorhombic, T tetragonal, H hexagonal, and then I have a lot of C's for cubic. Okay. Now I'm going to close this a second. I want to show you something. I'm going to go back to the AND operator and do my search again. So I'm back to that 2800. Okay. And let's click on, when you're ready, click on crystal system. And it starts out with the low symmetry. A, what is A? Anorthic. It's the classic term for triclinic because you got T triclinic, T tetragonal. So A is anorthic, which was the original term for triclinic systems. Okay. And then as we scroll down, eventually we'll see anything that might be monoclinic M. As we move along here, eventually we'll get to some orthorhombics, tetragonal, hexagonal, cubic, etc. Now, I go to the very end here. X. What's that mean? We don't have a unit cell. You know, just diffraction pattern, the data were reported, a unit cell has not been determined. So it's just marked with an X to say there's data there. But we don't know what the unit cell happens to be. Okay. Okay, I'm going to close that out. And in the same vein, if you did or, you're going to get a large number of entries because in this particular case, you have 318,000 entries. Why did it grow to 318,000? Well, it doesn't have to have all three, it just has to have one. And there's so many oxides out there that's why it grew up. And then the last one here called just. It means it has these three elements, but in any combination. Could be iron oxygen, cobalt, just those three in any combination. So you have more than the only. Okay. So these are different ways you can say, I'm studying a particular material. How do I do some data mining when I don't know the PDF entry number? This is how you start to narrow it down. Okay. Any questions? How do we do it all the time?
What if I want to do elements and like iron, cobalt, and cobalt all mixture, like or yeah, like and all something different area.
Suppose you did two different searches.
Yeah.
And then you had sort of a results. Okay. You can take two searches and combine them together. Okay, so basically what you're looking at is to say, I got these different searches here. I could do my and search, I could do my or search. I can now combine those because it keeps a record of the most recent searches you've done. You can combine those two searches. Now, another way, maybe, let's try something. There's another yes, no, maybe search. So let's say, I've got an example here that I'm interested in, has to have manganese. Okay. And it might have a few other elements, might have hydrogen, carbon, nitrogen, oxygen. It may or may not have. Okay. All right. And then I can say, do I want to say no to other elements? So what I've done here is I have to have manganese. I might have these elements and everything else is a no. That might be even an easier way to do what you talk about, is some yes or something else. It's another way to do it. Okay. And then sometimes I'll clear this. Oh yeah. Now suppose you're done with something. You can either reset the tab that you're on that's red or reset everything. Click one of these here. Now what tends to happen, I get in a hurry, I've done a search, I go to do my next search, I haven't cleared a tab and I get 0 results. I say, there's got to be something in there. Usually it means you have another tab open. But I'm going to say reset all. Okay. And on the reset all here, you might do something where you could say, I want to search like a composition. And in this case, I might say, show me all of the terbium iron phases. And it will list different combinations here. You can open that and then look at those particular. So there's some different things you can do here. The most straightforward is what elements I'm interested in for a particular phase. But if you want to combine a couple of phases, you can certainly come here and say, let me take a couple of hits here and combine them. Yeah. That help? All right, great. All right, so we've kind of explored how to do the data mining with particular materials, okay? All right, I'm going to reset everything. Back to the PDF form, and I'm going to show you something called subfiles. So in a subfile, we've had an expert in different material fields go through the database and break it down into smaller groups. We like to use as a sort of a equivalent. I have a bowl full of jelly beans. Someone says, well, you know, I like the purple ones, I like the red ones, I like the pink ones, whatever they happen to be. And you start to separate them out on some kind of common characteristic. And the most common is related to the kind of application or the chemistry of the material. Are they minerals? Are they clays? Are they polymers? Are they for forensics? Are they for cements? And so we've broken it down into 32 subfiles, 23 subclasses to help with your phase or your searching. So why would you care about that? Well, one thing is I'm interested to search the database. Let me search 1 million entries, or let me search 1,000 entries. And getting it down to 1,000 helps simplify the search process. Okay, so what we're going to do, we're going to do an example. I know on Wednesday, there's a tour to a cement factory. Is one of the things that they have here. If people signed up or not. So let's do a cement subfile search. Okay. So let's go back to the database. And you'll see this box in the upper right called subfile. Look through that and scroll a little bit until you find what's called cement and hydration product. Click on that. Now, as soon as I do that, a couple things happen. Notice the subfile title now turned red. That means it's active. Okay. Down here in my box of summary, subfile is now listed for cement and hydration. And the number of entries in the database is 1,620. Okay. So we've gone from 1 million to 500,000 of inorganic emphasize to 1,600. It's a lot better number to work with. Now let's suppose I'm interested in calcium silicates. All right. So I can do an elemental search to help. Well, so what would I do? I want to go to a Boolean search. And I'm interested in calcium silicate. So I want only calcium silicon oxygen. So I go only. And what 3 elements? Calcium, silicon, oxygen. Okay. So what happened? Well, we're down to 117 entries. Okay. Let's click on our search icon in the bottom left. And if I do that, I see that, yes, I've got calcium silicates, different chemistries. Now, does anyone here work with cements? A little bit. I mean, I've mixed some up and poured it on the sidewalk, but you know, in the cement industry, they really get into these cement phases and they have sort of nicknames for them. And one of them is C2S. Now, some chemists might look at that and say, oh, it's a carbon sulfide, but the cement people, it's 2 calciums, 1 silicon, and then the appropriate oxygen. Okay. So what we're going to do is we're going to be interested in C2S phases. So I'm going to close my result here. And I'm going to go to a new tab called Formula Name. Okay. So formula name. Now under this tab, you could put information about the chemical formula, maybe a mineral name, the IMA symbol, different things about it. And all of these have a drop-down menu. So let's go with the formula with the little drop-down arrow. And what are our options? Well, it could be any formula, chemical structure, ideal, analytical. For our purposes, we're gonna stay with any formula, okay? And contains elements, all right? So in that box, I'm gonna type Ca2, means I've got 2 calciums. Okay. And notice that already I went from 117 down to 59 hits. Now notice other things going on here now. The subfile is still highlighted red. Periodic table is red, meaning it's active. And now the formula name tab is red. And we have a summation down here in the bottom of everything we're doing. Okay. So quickly click on the search result. Okay. And you'll see here that I have calcium silicates. Different quality marks. Notice I've got different systems here. What does that mean about calcium silicate? It's polymorphic. Now, it's common in a lot of organic materials, inorganic materials. It can happen, it does happen. So it turns out there's more than one crystalline form of this material. Okay. All right, I'm going to close this result because I want to narrow it down a little bit more. And let's say that I want to work with data that has atomic coordinates. Maybe I want to import the data for retail refinement. So click on the box here that says atomic coordinates. All right, I reduced it a little bit. There's 51 entries, still a little bit large, okay? So let me do a little more cleaning up here. Suppose I decide I only want the star quality patterns. I want the best patterns. There are 2 options here on the quality marks. Oops, sorry. You'll see that all of them are checked except hypothetical. So you can either click one at a time on a box to remove the check mark, or if you hold down the control key and just scroll over the quality marks, you can remove them. So let's remove all the quality marks except for the star. And now you'll notice we're down to 16 entries. This is a much more manageable number. Okay, so when you're comfortable and you're ready, let's click on search. So if I look at this, what was I searching? Cement phases. Okay. I wanted calcium, silicon, oxygen only. I wanted the C2S type phase. I wanted atomic coordinates, and I wanted the highest quality patterns. So 1,500,000 down to, what do we have, 16? A much more manageable number now in terms of investigating, all right? And you'll notice, as I look at it here, I have the monoclinic phase, and there's actually 2 monoclinic phases, and an orthorhombic phase. Okay. So this is what you would look at. That's a couple things I want to show you here. First is, notice there's one with this blue star on it. So you can either double click on that entry, or you can single click on it, and where it says open PDF card, either way, you should be able to open it up, and you should see something like this. Okay. Now, the blue star means that the powder pattern was collected with an internal standard. And that gives you a sense there's even a little bit heightened precision or accuracy in that particular data set, because an internal standard was there in case you had any sample displacement or transparency issues. And the way you find that out, in the PDF entry, you'll see some information. This is the beta phase of calcium silicate. Has a name, Larnite, synthetic. But click on the tab here that says experimental. Tab on the left. But what do you see? Internal standard silk. Okay. Now, not everybody uses internal standards, and people do recut refinement to get lattice confidence, but this is just a indicator of one extra step that was taken on this data set. And I'm going to close that data set for a moment. Let's take a look at for ease, take the one the last one listed here, the 04, 017, 58, 41. You can double click on that or open that. And in addition to the information going on here, there's a tab called structure. If you click on that tab, as the atomic coordinates, this is what you would import into your recut refinement program to do recut. So either it could be a CIF file. It's automatically read into JADE. Or if you have Topaz, a STR file option is available to import it in. All right. So what did you do? You took the whole database, you funneled it down to a small number, a manageable number to do your data mining, to do your searching. And you can do this on any kind of material you're interested in. Okay, I'm going to close that entry. Now I've done this. And this is something you're going to, yes.
The next one when you say that has an internal standard, when we check the CMake profile, like some blue lines on top of the fractions, that there is some red lines and some blue lines.
Okay, so in this particular, if I understand correctly, and if I didn't, correct me. In this particular pattern, the individual reported they used an internal standard, so they've corrected any displacement in their peak positions. But in this particular entry, they did not provide the raw data. So the only thing that we're plotting here is the simulated profile. So the D-spacings that are reported here, or the peak positions reported here, are after the internal standard correction. So they've done a cell refinement, report the unit cell. They've also reported the D-spacings. And the star pattern means, since this is from an experimental pattern, they just didn't send the pattern or data to us, that the delta 2 thetas are less than X degrees. So we feel it's a high quality pattern. We feel it's a little bit better just because the internal standard was used for any displacement here. Did that answer?
Well, I don't know. So there is this.
But their close, their diffractogram is not normalized to 100, so there's a difference between measured and calculated.
Just like just this.
Blue and red.
Yeah.
Huh.
Yeah, that's exactly my thoughts, so we have normal, this is
Huh.
super sticky. We have normalized everything to 100. So the maximum intensity, as you can see there, is 100. So your measured and calculated are going to match up.
Okay,
I guess that's.
we agree, right? 3956.
0, 0.
One I'm motioning it's
You got
00033.
Yeah.
So there are like some blues overlapping, but some brights overlapping the blue. So I was just wondering.
right. Okay. Okay, funny. So if you show the D-spaced lines, what will happen is in the pattern, it's going to say, here's what peaks would be. But the blue will show, yeah, when there's overlap of peaks. And so you're adding more than one intensity there. So that's why that will show up to say what's going on. And sometimes they may be so close that they're not listed. Sometimes they will be listed. Anything else to? Okay,
Thanks.
all right. So I'll close this. Now, the problem here is that I've done this and I say, hey, Tom, this was nice, add it down to 16. I don't want to have to do this every time I get on the database. What can I do with that? So what you can do is if you highlight the first one, hold the shift key, click on the bottom one so that now they're all highlighted. Okay, right click and say add custom PDF set. I'm going to do that. I'm going to create something new. And my new one is going to be ICS CA2 cement. You can call it whatever you want to call it. Okay, this is just what I'm. Again, you can call it whatever you want to call a name. I say, okay. Okay, now I'm going to close my search result. And notice now you should see under your subfile, ICSCA2 cement, or whatever name you call it. So in the future, if now I hit a reset everything, and I click on that, it opens up. So every time that I want to now use this to just say, I only want to search these 16 phases, 17 phases, and it doesn't have to be all of the same phase. And this is where this question earlier about, can I combine some searches? Or can I list different entries that I want to include? So you could have multiple types of materials. I'm looking at a clay type sample, and I know I'm going to have these 10 minerals all the time I want to search. You can put those and call that my mineral for my clay. Okay. All right, how we doing? Okay. Yeah. What's that?
In the custom list, it didn't work for them.
For nobody? Oh, yeah, I'm on the. Huh, and I'm on the, because I'm on the same remote desktop server. Hmm. Okay, I've made a note of it, but.
So it just.
Okay,
This one I already did it a couple of times, so it's already doesn't show that on this. Should appear big over here. Yeah, there's a.
yeah.
Yeah.
All right, that one I don't have an answer to.
And I might play the lottery then.
That logged in first, so you've got all the bandwidth and all possibilities.
No, so let me check into that. Because that,
Yeah, cause I thought that maybe it's not enabled for them, but.
No, it should be enabled.
Yeah, so, Carlos, you're the only one who was able to do it.
Well, yeah, I saved it, it appears.
Yeah, then everyone else couldn't, right?
but that's,
Okay,
but everyone's got a different login.
yeah,
Huh, okay, I've got a note here. I'm not sure the answer, but we'll get an answer.
Yeah, I would next step is to show me how to get the numbers set.
Okay, all right. Okay, Let's see what we got here. Just a little bit. Okay, I'm gonna hit reset all. Just to make sure everything's clear. I'm gonna go to the periodic table. And so again, we have a number of options in this area here. Let's click on one called classifications. And probably of interest to this particular group, there are a number of ways we can classify different mineral species. The mineral classification, the first one listed here. This is a classic classification that went from several years from Dean Smith at Penn State. The tendency is migrating and had migrated to MNDAT classification, okay? And if you're involved with zeolites as well, we have classifications there. So let's go to the stunts MNDAT classification. It's about 90%, what?
If anyone's involved, utilize the next PDF 5+ mid-year release should have every zeolite code and every zeolite that is in the ICDD database. So you will be, if anyone working with zeolites, would be able to get any of the frameworks that you may want.
Yay! All right. Let's go to the stunt MNDAT classification and click on sort of the plus next to the number 2 for sulfides and sulfur salts. And you'll see that within MNDAT, there are some different classifications here. What I want to do is expand this a little bit to see it a little better. I'm going to go on group 2B. And then 2BA. So what do? We went to the stunts MNDAT. I expanded group 2, expanded to A. B is now my expanded area, sorry. And so I'm interested in 2.BA. These will be compounds of copper, silver, gold, and sulfur sulfide. And it says there's 230 different options there. So if I click on result, I've got a large number here. Now you'll notice, like this is copper, selenide, telluride, cellulite, it's in the same class. But I'm interested only in silver sulfide. How do I do that? What do I need to go back to? Periodic table. So let's close this. Result. And you'll notice my classifications tab is now red because we're using it. I heard let's go back to the periodic table. What am I interested in? Sulfur and silver. And make sure that we're clicked on only as our Boolean operator. And now we're down to 14 entries. And whenever you're ready, click on the search. And now I have just silver supplies. Okay. So particularly for what we see, particularly people studying minerals, mineralogy and such forth, the classifications really with the MNDAT is really where everything is directed towards that. And so we're adapting that. So we have most of that classified. We're working with MNDAT, so we're hoping that in the mid-year release that will also be 100% complete. All right. Now, I'm not a mineralogist. Anja is. And so, you know, the mineralogist will really get into these. Oh, it's a 2BA. That's a great. It helps them, and that's what we're here for to do. All right. Does anyone here do clays? Yeah, I hope so. Okay. All right. let's go to reset all. Let's go to the tab that says crystallography. Okay. Now here's a case where maybe you know something about the crystal symmetry, the crystal system, maybe even you've indexed the unit cell. Can I find something in the database that helps me get there? All right. So let's first start with space groups. All right, there's an area here called space group, and if you click on the drop down, either you can put in space group symbol, space group number. Does anybody deal with modulated structures? Smart people. If you're dealing with modulated structures, we do have those in the database. Okay, there are a few minerals that show modulation. Traditionally, people will work with symbol or number. I don't know, work with them or not, but there's a tendency, some people know their space group symbols. FM 3 bar M. Someone else will say, oh, I'm space group 225. I mean, just different people, what they know. Okay. So we're going to work with something here to say, all right, suppose I'm interested in cubic materials, and I'm going to work with space group symbol for now. Okay. And what I know is that it's body centered. Now, body centered uses a symbol called I. Now, anyone looking at that would say, why isn't it B? It's German for something that something that means body centering, whereas B could be B face centering. Okay. I didn't invent space groups, so I go with what the convention is. It's I. So in the database, the inorganic emphasized 64,197. Now, if I say, you know what, I'm really interested in body-centered cubic materials, I can click on the crystal system, cubic. I'm down to 16,000. Okay, so what have I done? I know it's eye-centered. I don't know the specific space group, and I know it's cubic. Okay. Now, if I say I know the space group, I am 3 bar M. Okay. So the M is along 100, the 3 bars along 111, and the other M is along 110. Now, how do I represent I M 3 bar M? Well, I'll put the M for the mirror, -3 for the 3 bar, because we don't have a convenient way to put 3 with a bar over it, and then M. And you'll notice now I'm down to 3,322. So what do I have here? I have IN 3 bar M cubic. What happens if I click off of cubic? I have the same number. Why? Once I got down to the space group, the specific space group, by definition, that meant it was cubic. So putting cubic in there now is a redundancy if I know the whole space group. Okay. Okay, so far. So again, this is if you want to search certain symmetry, certain crystal systems, and you do again have the option, give me cubic crystal systems, this space group, and I know it has a certain element in the sample, reduces it down. All right. Okay, so let's clear this, reset all. And let's say that you have some diffraction data and you've done something called indexing a pattern. How many have indexed a pattern? All right. So indexing means I have diffraction peaks, and from those peaks, I try to determine the unit cell, the A, B, C, alpha, beta, gamma. It's called pattern indexing. And it's the first step of trying to do a structure of materials. Okay. So let's say I collected some data and I've come up with what I believe is a unit cell. Okay. So my unit cell, I believe, is orthorhombic. Okay. And I'm gonna give you the lattice constants. And again, and just make sure we're all on the same page. Is everyone familiar with the lattice constants of a unit cell? No? All right. So if I have a unit cell. Some kind of box that's around my structure. And I have a length A, B, and C. Those lengths are the lattice constants. And then I have my angles, alpha, beta, gamma. And everyone likes to work with cubic systems because A, B, and C are all the same. Alpha, beta, gamma are all 90 degrees. When you take material science course, people come out of it thinking everything's cubic. When in fact, there's monoclinic, triclinic, other crystal structures. So as these numbers change, you go to different crystal systems. In orthorhombic, the angles, alpha, beta, gamma, are all 90 degrees, but the lengths A, B, and C are different. And that's how we designate it. So it'll show more diffraction peaks in a cubic pattern. Okay. All right. So I'm going to say I think I have something that has an orthorhombic unit cell. And I'm going to put some lattice constants in. So I'm going to put 9.8 angstroms and plus or minus 0.2. That's for A. Okay. B, I'm going to say is 12.2 plus or minus 0.1. And finally for C, 5.8 angstroms plus or minus 0.1. Oops. Sorry. Okay, so what do we got? I believe I have something that has an orthorhombic crystal structure. And I found these lattice constants, okay? And now I'm going to say, I think that it has a primitive unit cell. It's not face-centered, body-centered, any kind of centering there. So I'm going to put P under my space group. I don't know which space group, but I'll put primitive. And I've got 8 hits. When you're ready, hit search. What do you think I probably have? Some kind of a lead oxyhalide. Now, if I had elemental analysis, like X-ray fluorescence, I'd easily confirm was there lead. And I'd easily confirm is there bromine and chlorine. But I'm pretty comfortable that this is what I have. It's just another way to identify certain materials. Okay. All right. Just another tool, another option. All right, I'm going to close the result. And I'm going to reset everything. All right, what time we got here? So they said lunch was at 12:30. So how we need to stand up a second and breathe? Or are we okay? Okay, all right. So 20, 25 minutes and we break for lunch. Okay. All right, let's do okay. Let's go to our periodic table. And we're going to actually plot a little bit of data results that we're getting. I'm interested in looking at brass. Brass is copper zinc alloys. Okay. So I want to find phases as a only with copper and zinc. And when I do that, you should get 59 entries. Okay. Now, if I open up the search result, bottom left, what I see here is I have a variety of different crystal systems, which means I have different types of brass. I'm interested in a specific cubic brass. So how do we reduce this? Let me close the result. There are two things I'm going to be interested in. This time I want to look at data for ambient temperature. So under the heading environment, I've clicked on ambient. Okay. And I'm going back to my crystallography. Now I said I was interested in a cubic material. And in fact, I'm interested in a specific space group. And your choices are the symbol FM3 or the number 225. All right. So do you decide if you want symbol or number? I'll go with symbol FM minus 3M.
I'm gonna write it forward, so first you probably see the line. Okay, you can just go ahead. Just continue.
Oh, wrong line, sorry. Okay. And you'll notice I'm down to 18. Okay. So far, so good. All right. Let's look at my search result. I got 18 here. And you'll notice in the column under system, it all says C for cubic, right? Well, what if I wanted to see what the space group was? I can add a column. So move your cursor over to the fields text. Okay. Click on that and sort of move your cursor down to crystallography. Move over and you can click on crystal space group. And you've now added a column to your results. Now, they're all the same space group, so it's not telling you a whole lot that you didn't know because this is what you searched. But suppose we had our first brass search where we had different types of structures, and the space group could have been used. Right? But I want to get a sense of how does the lattice constant change as a function of the amount of copper or zinc. So I'm going to add a couple more fields. Click on the fields again. Come down to formula name. Move over to the very bottom where it says atomic percent and click on that. So now I have a column that I've just added that has the atomic percent, copper, and zinc. Okay. But I said I want to know versus the lattice constant. So let's go back to fields. Let's go back to crystallography. And if you look where it says crystal cell A, click on that. Okay. So I've added 3 additional columns now. Space group, the atomic percent ratio, and the unit cell A. All right, and I could continue to add more if I want. All right. So now I'm going to come under the text that says tools. Click on that, please. And click on create a graph. And on my x-axis, let's go for the scroll a little bit here. Find the atomic percent. And by default, it will list copper. You could certainly put zinc in there if you wanted to, copper. Okay. Now for the y-axis, click on the down arrow and go to the extocell A. That's the crystal unit cell length A. So what am I going to, what am I going to do? I'm going to make a plot of the atomic percent copper versus the crystal cell A. And when you're ready, click on create graph. I'm just going to expand this a little bit. So what do we got here? We've got 18 entries from multiple people. So we know everyone's data wasn't collected exactly the same. But we do know that we can see a very nice trend that as the percent copper increases, the unit cell, the lattice constant decreases. Okay. So this is a way using the database of being able to look at expansion coefficients, look at Vegard's law type effect. If I right mouse click somewhere here on the plot, I can show a linear regression. Right mouse click again, quadratic regression. One more time, cubic regression. And you get some sense about the data. Excuse me. Now, one of the things is that because this is collected by multiple people, and we know everything's not exactly the same in the experiment, that's certainly why we see a little bit of variability in the data, but it's pretty good. Gives you an idea of what's going on. You can do the same thing in the database with non-ambient data. We have the same option. If you're looking at non-ambient data, you can look at the thermal expansion coefficient. Particularly useful if it's not a cubic material. You can see it for C, you can see it for A. So this is just another way to work with the database. Okay. So you're taking diffraction data. It has the unit cell, has the composition, and you can get a Vegard's law type effect. Okay. Questions? And the other part of this was understanding how do I add columns? If I'm interested, like mineral name, I could add that. Now, what do you do when you want to remove a column? Go to that column heading, go to crystal cell with your cursor, right mouse click, and just say remove. And that column will be gone. Okay. Atomic percent, remove. Space group, remove. And you don't have to remove them, you can leave them if you'd like to. Okay. All right. With the time we have left, let's close this result. Let's reset everything. Go back to my periodic table here. Let's take a couple minutes to show you some new options we've added for microanalysis, composition graph, Raman search. So let's start with those a little bit. Okay, composition graph. You can put in, excuse me, 2 or 3 elements, and the little dots will represent all the entries in the database. I did forget to show you on that plot for the brass. You can click on any one of those dots and it will open up that PDF entry. we'll show it here. So if I put in specific entries in terms of elements, I can get sort of this composition type graph. So this is one for aluminum, silicon, oxygen. Okay, so let's kind of go through this example together. All right. All right, sorry. Okay, so I've made sure I reset everything. I'm going to click on the little triangle here, composition graph. Okay, so click on that, please. And let's click on 3 elements: aluminum, silicon, oxygen. And you should kind of get something that looks like this. Everyone see this? Okay. So what's it doing? It's saying that if I look at the aluminum, silicon, and oxygen, and look at the different possible combinations from a composition point of view, these are all the phases reported in the database. Okay. And I can either do it as atomic percent or weight percent. So the default lines here run along 50, 50, 50, but you can move your lines, or you can just say, show me the aluminum line at 33%, for example, maybe silicon 33. Where would I put oxygen? 33. You can move your line around to see what's my composition of different things. In addition, you can always reset this. And let's put our cursor on this sort of this dot that's almost, not quite, almost in the middle of the triangle, okay? And click on that dot. Sorry. Now what it will do, it will give you a PDF number. Now the reason this pops up is sometimes with one composition, there's more than one entry, so it allows you to select the one you're interested in. Highlight that entry and say, okay. And it will open up the PDF entry for that particular phase composition. And then at this point, you can see, aha, this is a zeolite, SOS-9, the composition information, and it gives you any additional data that's available for that particular phase. Okay. And the same thing works if, for example, suppose I was only interested, okay, so I'm going to close the entry. Let me reset this for a moment. Suppose I was interested in just silicon oxygen. Then you'll see that it'll just basically be a binary, and it'll list the silicon oxygen phases. And yes, oxygen is in the database, it's frozen oxygen. All right, so just a way, if you've got certain, like I say, a certain composition, you can see what the distribution is. Okay. All right, let's close that. Let's click on the microbeam analysis. So I know, particularly in the minerals world, you used to like a microprobe to look at a single particle and say, what's the elemental composition of that particle? And they like to see, hey, I've got this green particle in this red matrix. What's that green particle? And they go in and you do the elemental analysis. All right, so in our microprobe analysis, you can actually put in your elemental data and see, are there any diffraction crystalline phases that match that elemental data based on the composition. So there's a couple ways. One is you can import the data, or you can manually input the data, okay? So the first one we're going to do is we're going to manually input some data. Let's go down here. Right here?
Yeah.
Okay, all right. Sodium oxide. Now, keep in mind, you found sodium in your microscope, but I know in general for minerals, they tend to put it in the form of oxides. Okay, so we're gonna go 11.8%. We've got Al2O3. And that's going to be 19.5. And we've got SiO2. And that's going to be 68.7. All right, so let's do this together. Let's go back to our database. Let's go to the make sure. I'm going to just make sure that I've reset everything. I'm going to go to the icon that says micro analysis. Click on that, please. So our first element was sodium. We're going to put in the form of Na2O. You can also do it just as the element. If you do, sodium, then you would do aluminum, silicon without the oxygen. You can do either way. Okay. And the amount we had in there, we said was 11.8%. Okay. We'll tab Al2O3. And we said 19.5%. SiO2. And we're going to put in 68.7. Okay. Now, when you're happy with that, you'll see on the menu for the microanalysis, it has its own little search tab. Click on that, please. Okay, so now it's going through all the data in the database, doing a search for phases that have that composition. Let me expand the result. And so based on the elemental analysis, it looks like a pretty good chance you got albite. Okay. Sodium, aluminum, silicate. Okay, so this is a way. I don't have enough sample to run my diffraction pattern. I got microprobe data. I've got some elemental data. Let me at least see, do I come up with a match? Now, one of the things my observation has been in this microprobe analysis, they get in there and it'll have 0.001 lead, 0.001 chrome, like that. You don't keep on, we're searching probably on more than ideal formula. But if you want to ignore any elements, if you might import some data, you have a bunch of data, you could say ignore certain elements if you wanted to. And you can also either make very tight or very broad search windows. But the idea, I had elemental data only. Reset that, please. Now, how many people enjoy typing in a whole bunch of elements? Right? All right. Wouldn't it be better if you could import it? Yeah. All right. So let's go to File, up there in the upper right. Import composition data. Does everyone see that? Okay. And let's find out, because depending upon how you're set up there, are you at this point or is there another folder? Where are we at here? Okay, so click on ICDD PDF demo folders. Click on documents and go up. Click on the green arrow, yeah, there you go. Click on that. And click on ICDD PDF demo. Raman microanalysis. Nice. Okay. Click on the Raman microanalysis folder and go ahead and import the file.csv file. That's pyrope. Now what it's going to do is it's going to import that data. Okay. And then upon importing the data, it also is going to try to do the phase ID. Now, is this a shock? The file name was pyrope. What did we come up with? Pyrope. And this is for demonstration purposes, obviously. But the intent here is that what you get is, here's what the microprobe gave us in blue. And we've got the PDF entry. Yeah, they're pretty close. Is it perfect? Well, perfect match would be 100%. What's this mean? Well, this is the real world. I mean, this is real data, and everything is not, SiO2. It might be SiO 1.98, because a little dopant is in there or something. But again, it's a way that we've imported the data. Now you'll notice, in addition, you've got the major elements. Notice that, for example, TiO2 is at 0.47%. Yeah, this will change, the allocation a little bit there. If I wanted to, I could say ignore the TiO2, and this probably raises this up a little. But the intent here is, I've got my microprobe data, I've got my XRF data, I bring it in, and what I've got here now is a way to identify that single grain of material. All right. Okay, last quick example, and then it's time. All right, guys are a great group here. All right, let's do reset all. And the last thing I want to show you is this one called Raman search. And Raman, what's that have to do with powder diffraction? Well, actually a lot. The minerals folks in particular, and this was the driver for this, oftentimes are more and more using Raman to help with identification, particularly out in the real mine. They have these handheld Ramans. They go up, they see some vein going there. Is that my quartz vein? I bet I'm getting close to gold, or something. So what we have started is a program with Paul Bartholomew at Quinnipiac University, Jeff Post at the Smithsonian, and Bob Downs with the RUF database, of putting Raman data now in the PDF5, PDF4 databases. Okay. So in our first year of entries, we're focusing on what we consider the top 600 likely minerals to see. We have 354 entries, and we'll be adding more this year. But the idea is that you can either type in a particular mineral name, see what the Raman spectra are, or import a Raman pattern and try to do a similarity index match. Okay. So you open it up, you can see what the Raman data look like, and these are all experimental data that have been collected. Tricky thing with Raman, the Raman people like to use multiple wavelengths on the same sample. So when that's available, you put all data for all multiple wavelengths in there. Okay. So let's do let's finish off with an analysis. So click on the tab that says Raman search. Okay. And our first thing is you're going to say, show me the Raman pattern of barite, barium sulfate. BARYTE. Okay. And we have 3 patterns that are there representing barite. One of them you'll notice has a little bit of strontium in it. One of the things that's been emphasized to us with Raman As you vary the composition just a little bit, you'll get Raman shifts and changes in the Raman. So we're trying to put those in the database as they become available. If I double click on the first entry, 10.001.0266, you'll see here that I have Raman spectra for 3 different wavelengths, 512, or sorry, 532, 514, 780. One of the things that Jeff Post and Paul Bartholomew are trying to do is get some kind of standardization in Raman. Because right now, it's not there. You know, different people, different wavelengths, different conditions. So hopefully, like powder diffraction, it'll be standardized. But you can say, I want to see all 3 spectra, or I only want to see the 514 as an example. And you can do a match. How do I do that? So let's go here. Let's reset everything. Little reset button. You see the fingerprint here? That's basically trying to do a fingerprint similarity index match. Click on that fingerprint right here, where there's a little fingerprint on the right next to the periodic table. And you should have the folder we were just looking at, Raman microanalysis. Is everyone okay? Let's go ahead and do M. I like that and say open. I look at the pattern. I'm comfortable that the background is clean. I don't need to do anything with it. So when you're ready, click on import. And so now what it's doing, it's going through the Raman database. It's going to try to find a match for pattern M, and it's found something called monticelite. Okay. Basically, it's a calcium magnesium silicate. Didn't get it? All right, see what you got here. Let's try it again. Make sure we're on this. I'm gonna reset this. So let's go to click on the fingerprint, import the pattern M_R100. Okay, good. Say open. Click on import. Monticelite. Yeah, yeah. All right, all right. And what it's doing is what we call a similarity index, meaning it's doing a sort of a graphical comparison of the 2 patterns. It's not a peak position like phase ID and powder XRD. It's the actual whole pattern matching. Okay.
So I can refill based on the database.
Well, the difference with read felt will look at how well did it match. Oop, let me adjust a couple parameters. How well did it match? Adjust a couple parameters. This will just be, here's the pattern. Here's the raw data. Here's the experimental pattern. How good is the match? And if it's a perfect match, you know, it's 100, 97, 98. So for example, it's showing a couple of monticelites, calcium, magnesium, sodium. And as I scroll down, you'll see, depending upon the exact composition, slight differences in intensity. And this is what the Raman people use to try to differentiate between. So it's very similar to forsterite, which is magnesium silicate. They're all in that family. And so you try to find which one's the best match. Okay. So the future of this is that we'll be adding more patterns. We'll be expanding it into more fields beyond minerals and putting correlations in there so that you can take your fluorescence data, diffraction data, Raman data, and put them all together to say, do I have the identification? IR is coming. We have permission to use George Rossman's IR data from Berkeley. But step one is get the Raman in there, and then next will be IR. Wow. Lunchtime. All right, you guys are a great group. Any last minute questions?
It's just a question that sometimes I face, like apart from the work of PhD that I do, the only geologists and mechanics review. So often I come to what I have in this powder.
Yeah.
Sometimes you identify like the main things that are easy to identify, and I always wonder how to use the PDF database to those bits that remain to still.
Sure. Anja's going to get into some of that.
Okay.
Okay. The phase ID part will be sort of next step. The database can be used to do that. JADE can be used to do that. Anja's going to get into it. I'll give you one little hint. Sometimes JADE can do this, does very well. Sometimes you can, let me search on one peak. I know it's a mineral. What's the likely peak? And you'll say, I have a peak at 3.5 angstroms, and it'll list what are the probables. In the database, there's also a component here under the diffraction tab where you can say I have a strong peak at 3.5 angstroms. Help me identify. And you can narrow it down because you can say, give me the subfile. I only want to look at minerals. I want to look at minerals, and I know I have these elements in it there. And you can narrow it down and at least get probable hits.
At least at this point, obviously, you identify all the peaks that remain. You don't know if that's actually that one.
And that's the tricky one.
Yeah.
And so sometimes you have to do a few perturbations of it there, but that's where JADE has some smarts built into it to help you even address that kind of. All right, lunchtime. You guys are a great group. I'm not sure how long lunch lasts. Do we know how long lunch lasts? It's not 4 hours. I know that. I don't make it's an hour, 45 minutes.
It's up to yourselves, it's not actively.
Well, what do you guys wanna do? Do you want 45 minutes or an hour? What's better for you? We don't wanna overwhelm you.
Well, we did that already.
Yeah.
Huh?
25 minutes.
All right, so tell you what. Somewhere around 1:15, we'll start to kind of gather together. Take a couple minutes. Now, I will say one thing. If the remote server is idle for a long period of time, it may automatically log off. If that's the case, we'll just log back on when we get in. There are a few power plugs around here for those who need to plug their computer in. Hopefully that'll help. Guys are great. All right.
Okay, so the plan was, as I mentioned, to focus on JADE. I'm gonna show you what JADE is. It's an extremely powerful software that's linked to our database. And I'm gonna focus on natural samples and clay samples. So JADE, as I said, is extremely powerful, and it's JADE has been in development for over 30 years by the MDI group, Materials Data Incorporated. They are now together with ICDD, so we are working together, and that's why our database is joined together with JADE. JADE is meant for primarily phase ID, but you can do data processing, viewing, different data manipulations, read-field analysis, and everything that you can do with any kind of, software, either from a company that, sold you a diffractometer, or softwares like GSAS, though GSAS has different options, but some kind of, whole pattern fitting and read-field analysis software. So since JADE is independent, it reads all files. It will, doesn't matter like who your vendor is, meaning like where your diffractometer came from, you can open these files in JADE and work with them in JADE. I'm gonna, I guess, yeah, we're gonna go through this, yeah. So JADE has capability for comprehensive data processing. It includes single peak search, which is something that you were asking about. We can do that in the database as well. Once you have exhausted all possible minerals and everything that you may have in your sample, and there's this tiny little peak and you can't tell how minor this phase is, if it's minor or not, you can use a single peak search in JADE or in our database, and it can be very helpful. So JADE is integrated with our database, and a very cool thing, which I'm gonna show you, is that you can, as Tom showed, creating custom files, subfiles in our database, you can create a custom search file in JADE, which comes in extremely handy if you're working with clay-rich samples. So, okay, I'm gonna show you JADE. I'm gonna show you how to create a custom list. I'm gonna show you certain features that JADE has that will help you figure out which clay minerals you have in your samples, and I mean whether you have clay minerals in your sample. And show you how to do quantitative analysis, like really quickly. We're not gonna delve into that because that's a whole workshop in its own. And then the toolkit. So now we'll spend less time on toolkits than planned, because I'm going to switch to the database and show you how all of this is done in the database as well. So some of the features, JADE has something that is called clay basal peak finder. And are you familiar with the book of Brindley and Brown? One of the I can't say first, but one of the, most well-known clay books. So this is a classic monograph published by the Mineralogical Society. And what they have is a list of most common basal spacings in clay minerals. So what you see in the book is something like this. You see, kaolinite basal spacing 7.2 says kaolinite is non-expanding clay, and it gives you notes a little bit about this type of clay or any type of clay, and it gives you, the range of where you could see the tallest clay peak. So that is back to here, something I'm going to show you, something that you can see in JADE. As soon as you hover, you need to select the clay cursor, and as soon as you do that, you can hover over peaks, and it will tell you all possible clays that have that basal spacing. Okay, so just a quick thing now that I know that you're not really JADE users. I'm pointing at here as something that we're gonna be working with. This is the oriented clay and the pattern matching toolkits. They are both very useful for samples that are clay rich. So, okay, now we can talk about, we can move to the database for a minute. We'll keep like switching back and forth, I guess, now between the database and JADE. As you've seen, database contains subfiles. So within the mineral related, we have a subfile that's called mineral related, and then we have these things that are called subclasses. So what we plan to do in very near future is create a separate clay subfile. So that will mean that that once you work with clays and you're working with our database, besides the types of searches that you can do now with clay minerals, you'll be able to select them based on for example, sample prep method, whether it's random or oriented, whether it was treated or not, glycolated, heated, air dried, and so on. So it's going to make clay research, I guess, using our database a little more straightforward. And then another thing that's gonna happen is a rock forming mineral subclass. So that's going to be very helpful once you're working with natural samples, because what we have, we're adding on average 120 new minerals per year, but these are now, they're not of economic value, of commercial value. These are new minerals that were found, in some, hydrothermal vent or something, and it's a very tiny mineral. It's nothing that can create some kind of mineralization, something that's going to be important on a very large scale. So once we have a rock forming mineral subfile, that's going to be very helpful for anything that you do. And if you're working with cements, you can join and do an overlap between the two and create your custom subfile that's going to be very helpful to you. Okay, so clays. The biggest, I'm gonna say, advance in like clay subfile recently is the addition of raw data. So we had some raw data from Dean Smith, who Tom mentioned earlier, from the 80s. It was added in the 80s, but generally clay minerals are so, as you know, poorly crystalline, not pure phases, and so on, and it's hard to add them in the database as something very specific. So now we've been adding, together with Professor Hillier, new entries into the database with raw data. So this is something that, you'll see these entries that don't have defined structures, but they are clays, and it is very helpful to have raw data because you can compare your data really quickly with raw data that you have in the database. Do you need to reset your connection, or can you open the database? Okay. So here's our subfile, and if you scroll down, all the way down, you'll get to mineral related. So mineral related, there's 48,338 entries. And then if we switch to clay, we have 356 clay entries. Now, if we say, let me see, clays with raw data, there's going to be 94. So if I click search here, I already have this set up. You guys don't. So if you do, you so far you have the first, second, third, fourth, and all these columns up to the crystal system, right? So what you can do is go to fields, go to ICDD filters. It's the first one. And then click raw diffraction data. Okay. So is everyone there? Yes, you can go to fields. All right. All right, I'm gonna reset all. Here in the subfile, scroll down to mineral related. And under mineral related, you will find clay. If you click on clay, you will get all clay subfiles that we have in our database, and that is 356. Okay. So now you have this button here that says raw diffraction data. And now you can click this button. It's where the ambient and non-ambient is, and below it, right above the Boolean. Okay. Then if you click search, you will get your search field. So now you want to have the raw data preview. You can go to fields here, ICDD filters, and that's where you can turn on raw diffraction data. Sorry? It does. Okay, perfect. Okay. So why this is super helpful, because as you know how clays are, you cannot necessarily distinguish a clay, like for example, you see a quartz peak, you know that that's quartz. If you have an oriented clay sample, you can look at it and you can just eyeball it right away. But if you want to compare it with the database, you can, you can narrow down the search if you need to, and then just scroll through the list of raw diffraction data files, and you can, choose several and based on your visual comparison. Okay? So then once you do that, you have like actual raw diffraction data here. Now, if you click raw diffraction data, it's going to pop up. What you can do is you can go to plots. You can choose to add a diffraction pattern or to import a diffraction pattern and also add a stick pattern. So what you can do here is a comparison between your sample and the sample that's in the database. I have an example here. So these are all Dean Smith's entries, and these are Montmorillonites from Arizona. So these are Montmorillonites that are going to be treated differently. So you can do an overlay of patterns that are already in the database. So you can compare how your sample, not your sample, how a sample in this case, like a Montmorillonite sample, acts depending on how it was treated. So now we're looking at a sample that was heated and a sample that was glycolated. And then if we want, we can add another one. So we can take a look and observe the difference between glycolated, air dried, and heated. All three are oriented, all three are from the same location, so same sample, different treatments. That is usually something that you would do if you're separating clay fraction in your lab and looking at specifically clay. This is something that you may want to do different treatments to make sure that you know what type of clay mineral you have. So this is once you're comparing samples that are in the database. But what you can do is go to plots once you open your raw data plot and say import a diffraction pattern. And now I don't have it. I mean, I can import a random diffraction pattern. Sorry?
It's not possible to have the
You don't have this option?
All right. I know, yeah, it's because you need to first open the simulator.
Yes, okay, so let me close this. So you want to open a diffraction data file that has a raw diffraction pattern, okay? So this right now is a heated Montmorillonite sample. So you can see the diffraction pattern here. If you go up here, it says raw diffraction data. So if this button is live, that means that there is actual raw data. And once you click on it, it will open the raw data, not the calculated pattern or simulated. This is actual measured raw data. And that's what makes it very useful, because this is real data. So your data doesn't have to be the same, of course, but it's going to be similar, So if you have, I don't know, a Montmorillonite, you can compare it to all of these other Montmorillonites. So once you're here, I showed you so once you're here and you click on plots, you have all of these different options. If you choose diffraction pattern, it will give you an option to put in a PDF number, or you can call one of the patterns that you looked at. And then you can say add. And what do you want to add? Do you want to add a simulated profile or an actual raw diffraction data? You want raw diffraction data. And it creates an overlay. So if you go back to plots and you say, I want to, instead of add data from the database, I want to add my own data and compare it with what we have in the database, you're going to click on import and then go to where your data is and add it. I'm just going to add a random thing because I don't have anything that really, okay, works here, but it's going to give me a sieve option, which I'm gonna show you how you're gonna work with this in a minute, and I'm gonna say import. And what is happening? I was looking at copper data that was analyzed with a copper tube, and I'm importing data that was analyzed with cobalt. So now we have two different wavelengths, and it says the graph radiation has been changed to cobalt because that's yours. You want to compare it to what you have. You know, if you have copper, everything is going to be copper. But yeah, so if you don't use copper, this like the database will know. Okay, so this is nothing that we really want to match up. But even though, because this is a mixed sample, but we can, you know, right away take a look and say, well, I do have montmorillonite. You know, the green peak is my data and the red is montmorillonite. All of these are montmorillonite, but I can go back to this pattern. I can't open it from here, but I can open this this diffraction pattern and take a look and see what kind of treatment it had, and then know that that matches the montmorillonite that I have in my sample. Okay. Any questions? All right, cool. Okay. So super useful feature. Okay, so that was jump to the database. Now let's go back to JADE. Okay, we've seen this. All right, so I'm gonna show you now how JADE does search match and how you can analyze your data in JADE, and all of this that I'm gonna talk about is kind of focused on JADE, but it's a very similar principle, if not the same, in our database. So it applies to both. JADE has an automated background fitting, our database doesn't. So that's something that I'm gonna show you. In JADE and in our database, results are based on the figure of merit. It's just different. JADE says lower is better, our database says higher is better. But in our database, you will see a color-coded list. So you'll know what your matches, you know, what your best matches are. Sort of like, you know, green is best and then red is worse, that kind of thing. Offset is a huge thing. Once you're doing a multi-phase sample phase ID, JADE will figure out your offset and apply it. Whereas in our database, you're gonna have to give it sort of a degree of freedom, like how far it can you know, look left and right from your peak to find certain matches. And now why this is, and this applies to your questions. You're looking at natural samples. You have a database that has, like, what did we say, 46,000 minerals. So these 46,000 minerals, because this is all natural, maybe you have, doesn't matter, 2 pyrites that are supposed to be like super easy to identify, but maybe your pyrite is just for whatever reason a little bit different, and it's not really an offset, but it's a different, the phase is a bit different. So you still have to think of that and let the software have, you know, a certain degree of freedom to figure out that that is actually pyrite. you know? When you work with natural samples, I'm gonna say the most important thing is to have an open mind. So if you're with chemists, for example, you can't go by that idea, this is this, because it's not. It hasn't been created in a lab, it hasn't been synthesized, the conditions haven't been controlled. You know, you all know, like the same mineral collected here in Ireland, in the States, is going to be very different. That's why we have Raman, because you're gonna see all the minor phases in there and all the inclusions and all the, you know, vacancies and whatnot. So your diffraction pattern is not going to be identical, but it's the same mineral. So that's something that you always need to keep in mind. And then, yeah, we're saying here, can focus down to a single peak, and that's something that's very useful. So I'll show you how to do that. Okay, so we have subfile selection in both JADE and our database, and I'll show you how to import a specific subfile into JADE. And now, since we'll be talking about like different multi-phase samples, and if we have time, I'll show you how to combine searches in the database, only clay related search and then mineral related search. Because that is basically, I want to say, the most important thing that we've achieved here once you went with natural samples that are clay rich, is that you can do two separate searches or combine them. One is specifically clays, and then the other one is everything else. And that's, you know, because if you're doing like your regular search, you're looking at highly crystalline phases. It's like they're all going to be matched up. You have a ton of quartz. That's it. It's going to say quartz. It's going to say there's like some calcite, feldspars, whatever you may have, and it's done. But then if you have an actual clay file that you can search through, then you can match up phases that are not necessarily minor. They're just broad peaks that may not even appear, you know, obvious in your diffraction pattern. Okay, so we're not going into clay toolkit. Let's go to demo. And then we're gonna do the same thing in JADE and in our database. So let me know if you've opened JADE. Are we all good? Okay, so this is JADE. JADE will automatically open the last thing that you worked on. So I'm just gonna right click here to show you that we have now 2, 4, 6 different little squares, and each one of them has its own menu. So in this case, I'm clicking on the menu that will clear my plot, and that's what I'm gonna do. I'm gonna clear the plot. So I assume that this is the screen that opened up for you guys. Okay. So what this says is that everything is clickable basically, and then it says, so don't panic, go ahead, boldly click away and scroll away. So you can click and scroll everything, every mouse button has a function. So all of these tabs here are the same menus that you can see here. Okay, so let's start with, this is JADE. I'm gonna open a file. You guys have, do you mind that I keep saying you guys? Sorry. Okay. Force a habit, sorry. Okay, so if you go, I have to look at 2 screens now, sorry. If you go to your folder in on the server, you will see Anja something. I'm not on the server, so you'll see Anja clay, something like that. So if you open that, you can go and click on Argentina rock. Sorry?
I was supposed to have access to the sort of computers.
The same way you search, okay, so let me see how that's gonna work for you guys.
I'll go to.
Go to File, Start. Oh, stop. Click on Start, open new folder. And, okay, so that's gonna be J demo, go to the doc, okay, so doc, like documents. And then, okay, so it's gonna be in the documents, so then you can open bulk samples. And then Argentina rock. Okay, did everyone get this?
Another PC.
No, documents. All right, so the reason why this is called Argentina rock is because when we started working with clays intensely, one of our board members, who's from Uruguay, came to the meeting and gave me a green rock and said, here's the clay from Argentina. So that's all I know. And then I, like, what do you do? I looked at this rock and it's super soft, like you can crumble it in your hand. Oh, I'm just talking. Folder, yes, bulk samples, Argentina. All right. So if you're just working with Jade and you have your samples, you can just drag and drop sample here. And it opens. Okay, so yeah, that's the story. I just got this greenish rock that's very soft that I know is from Argentina, and that's it. So like nothing else I knew about it. So, at a first glance, you're gonna be like, hey, is this quartz? Yes, but no, it's not. You can take a look and see that it's not, exactly quartz. So now, if you go to, okay, wait. First of all, let's talk about subfiles. If you take a look down here at the bottom right corner, you see it's probably going to be like in pink letters which subfile you're using. Once you click on that, it opens up this menu, okay? So you have an option of searching all subfiles, which Tom pointed out, it makes no sense. I mean, unless you have no clue what you're looking at, and then maybe that would be sort of like a, shot in the dark if you get it right or not, but it would be helpful. So you always want to try and narrow down your search. When you're searching for minerals, especially, and you say you don't choose a mineral subfile, you're going to get a ton of alloys, for example, something that was, synthesized, created, because some peaks are going to match up. That's bound to happen. So you want to focus specifically on minerals because it's going to make your life easier. So here, metallics would be alloys if you just wanted to focus on alloys and so on, but I have chosen mineral subfile. So if in your case, if that wasn't selected, select the mineral subfile. Okay. So now we have a mineral subfile selected. And Jade has a similar, if I click here, if we go to phase, you get this menu that becomes live. So here you have a chemistry filter where you can work in a similar way as you would do in the database. So you can choose some elements and exclude others. You have options to select unit cells, cell lengths and so on. Sorry?
There's no button on the tool.
Go to phases. Okay, so this is the beauty and also something that may drive you insane with Jade. If you are in scans, this is grayed out. So if you go to the next tab and click phases, this menu becomes live. And now here you can give it a 2D offset, how much you want to give it, you know, freedom to search around 2D or 2 theta. Generally, we don't want to give any software freedom to search like a large despacing error, because that can lead us to very, very wrong results, because the despacing is in angstroms. So you give it, you know, some freedom and it's gonna search this like huge area. So you generally want to do that in 2 theta. So this is where your chemistry filter is. If you want to, you know, choose to use it or not, you can. This is the chemistry. And then the next tab is the unit cell, where you can input some of the parameters and limit your search if you want to. So as I said, background is automatically set or detected. So now if you click this BC, you see how the background is set. And generally it's always done pretty well. So now this S/M button is a search match button. So it's going to search all these phases and match them up with whatever it thinks you have in your sample. So I'm going to click this. And it's going. Okay, so here's your list. The first thing I'm looking at, if you zoom in accidentally or on purpose, you can just double click and you will zoom out. Are we all good here? You can interrupt me whenever. Okay, so our first thing is calcite, and that is for sure, that is calcite. So then I have something that is fairly odd, and it's telling me that it's matching up really well, this one peak, but I don't believe this. Okay, so when the calcite wasn't chosen, I had a little more of these options, but as soon as I chose calcite and it matched up these major peaks, now it's giving me something that I don't necessarily think it's valid. Quartz, sure, of course. I mean, that's something that makes sense. So now what is zinnwaldite? I don't know. I Googled it. It's an extremely rare mineral. So it is a clay-like mineral. It's a clay mineral, but it's extremely rare. So I'm just not going to go with it and say like, sure, I have zinnwaldite, because it makes no sense. Why would I, you know, in some like, you know, big.
Well, unless you have the chemistry with you, that's how I interpret.
Well, exactly. That's what this is. You're right. Okay, so one thing that we should point out, what we're doing here this whole time is just showing you how you would go by if you only had diffraction. Because when you get to like the smallest phase, which we're talking about smallest phase, not necessarily, but smallest peaks, if you have Brahman, if you have, you know, you can figure out what that is. If you just have XRF, you're not necessarily going to figure out what that is, you know, especially if that's a silicate something, you're not even going to see anything, you know. So it's tricky. And then diffraction is going to be one of your major tools always. But when you're doing your own research, you're going to have different analytical methods that are going to help you out with, you know, determination, with your phase determination. Okay, so I'm going to say no to the zinnwaldite. And then yes to analcene, because I figured out that is in there for sure, and that's a zeolite. Okay. How do I get rid of this, Zoom screen, Zoom thing? Cause I need to look at the small screen and I can't get rid of this bar. Do you know? This, I wanna get rid of, you can't see it. Can you come over for a second, please? Cause I can't work at this screen because it's in the middle of it. Oh, this one, you know? That's on this computer.
That's on that one.
No, it's that bar. Then right click on it. Try float, oh yeah, right click. That one.
There we go.
All right, great, thank you. Okay, now I can see what I'm doing, sorry about this. Okay, so analyzing, yes. So now. What we have, some pledge, maybe some feldspars down the list, and that all makes sense, but as we, you know, when we take a look, we have a lot of stuff here that we still don't know. So this is the moment where you want to combine your searches. So how would you go about that? I have a clay mineral list here, but when you want, I'm gonna show you real quick. You want to go to the database tab here in JADE and then click on PDF data mining. Once you click on that, your database is going to pop up and you're going to see the PDF entries can now be added to MDI JADE. Okay, did you all get that? So as Tom pointed out, always reset your search because it may get you down a lead you down a strange path if you don't reset your search. So now I've reset my search. I've selected clay again. So I just want to work with the clay subfile and I'm going to click search and I'll get the list. So now we have this button here that says add to MDI JADE. If I click this one, it will transfer just one entry, and that's not what I want. I want to go to file, and then there's going to be this option, add list to MDI JADE. Do you have that? Okay, so you click that, and then you go back to JADE, and here is your list. So let me show you again. I'm going to clear this out. So there is no list here. If I go back to the database and say file, add list to MDI JADE, and then go back to JADE, I have this list in the corner here. So this is going to be your temporary list in JADE. Whenever you're doing like a secondary search, things are going to appear in this list. You can always clear it by clicking clear or trim, but in this case, we want to keep it. So I'm going to go to the save button and say save this hit list. And I can now name it. I'm going to call it test list. You can call it clay or whatever you want to call it. And then just waiting for, then you click OK. Once you clicked OK, you see there's this menu that pops up here and says, here's your test hit list. So now this is your custom list. You can choose that. You can clear this or not. I mean, it's better if you clear it. So now we have cleared this list. We have our test hit list here, and we've only chosen 3 phases.
Can you repeat this last time, or I know that it's just
Yes. Okay, so we're here. Okay,
And you go first to J.
did you? Where's my Jade? In Jade, did you go to database and click? All right, so now you're here. You searched for clay, is that right? Okay, you want to search the clay subfile. So you want to go to, you look at this subfile box, scroll down to clay. Okay. Now, close that, so you have something else open. Now you want to click search. X out of that. Yeah, X out of that. Just as, yeah, hang on. Don't, let me try and click on this. Okay, there it is. You have to click like a little bit to the left, and now you have clay selected here. So now you want to find your search button and click search. You know, X out of that too. Like close it. And now reset the search. And now click clay again. And now search. Okay, so now you can go to scroll up. Up all the way up. To file. Here's file. Add list to MDIJs. Okay, so now your list is here. Okay, so now we're back to the list is in the corner. All right, let me do this again. File, add list, Jade. Now I'm gonna go back to Jade, and now the list is here in this corner. Now you have a save button. Can you see it? It is like right here. So you want to click the save button and just give it a name, whatever you want to call it. And click OK. Did it work? Okay, so then this menu here is going to pop up. And that's where you're going to have your list. And then you can choose that. So clear this list if it's still there. And then if we go back and look at what we've chosen, we've only chosen 3 phases. Now, there's a bunch of phases here. There's 79 phases. We don't want them. You can right click. You don't have to right click. You can hover over the phases tab and double click. What it's going to do is going to cut everything that you haven't selected, and it's just going to keep what you have selected, okay? So now we have our clay list, and we want to search just that. Okay? All right, so if you take a look at this menu at the bottom of the list, there's going to be a magnifying glass. And that means that you once you click it, it says search match this list. So you click this and it will not consider anything else except what's on this list. So now as you click on these entries, you can see where the peaks are, okay? So this says glycolated right away. I'm going to say no, it's not, because I know that this is a bulk sample and it hasn't been glycolated. So I don't want to choose that. But it's telling me that I have an halide smectite 7030. It's one of these 2. I can right click on one of these and then go to view details. And what it's going to show me is a version of a PDF card. So I can take a look And I can see that this is an illite smectite, 70-30, R1 ordering. If we have time, we'll talk about that. And that it's been heated to 300 degrees, see, 300 Celsius. So I'm gonna say, okay, I'm gonna accept this. Not because my sample was heated, it hasn't been heated, my sample was dried at like 100 degrees, but because this matches up really well. It doesn't have to be what I was saying before. When you're working with minerals, you don't necessarily expect to have an exact despacing. So I can say this is not a glycolated sample, which is 100% true and important, because I don't want to match up sample that was treated chemically with the sample that hasn't been treated chemically. But now my sample was heated to 100 degrees. This sample has been heated to 300 degrees. All water is out from both of these samples. They're similar. So I can say, okay, I'm never going to say, if I write a report or something like that, I'm never going to say, hey, this sample has been heated. This is an illite smectite that was heated. No, I'm going to say this is a clay mineral that corresponds to the despacing of this illite smectite, okay? So that's your logic. Does that make sense to you?
Can you show again how, like, in the moment that we imported from the database, we charged this and then you deleted this list that was in
The little one?
yeah, like
You see this clear trim button here?
just so many buttons at the same
I know,
time.
JADE is very overwhelming. That's why we're doing this like very slowly. So do you see the clear trim button? Because this is a temporary list, you just click that and it's gone. So now I'm gonna repeat this search, and then we were looking at this one. I'm gonna say this one works. And I'm gonna say, all right, this is matching my sample. So this is your logic. Now it's giving me more options. And now it's giving me a different type of illite.
So you move the next to the.
I drag and dropped it. I went like this. I clicked on this. I just dragged it. See, I'm dragging it over. And then you just drop it. And then I put in, now I have a wrong thing here that says glycolated, but I don't want that. Just hit delete button. I'm just gonna hit delete and it's gone, okay? I'm sorry, what? You double click here. Okay, so I'm saying that we have this one. I'm dragging it here, okay? I'm just gonna drop it and there it is. Okay, so now if we take a look at our diffraction pattern, we have a bunch of peaks that have not been covered, right? So I can again trim this list and then go back to search match and click that again. Now I'm getting a different list here with things that are possible in my sample that are not clays, or some may be clays. And I want to go through this list and figure out what I have, okay? So I'm going to say, okay to albite or anorthite. I'm gonna say okay to anorthite. And now I have my feldspars, but I have a bunch of stuff here that I have not determined. Okay? Are we all good? Double click here where it says phases, double click. Okay, so now you have that. Okay, sometimes it will give you like a similar option, so you can go further, and JADE sort of thinks ahead. It is very overwhelming at first. Then you learn to love it.
Question, how did we get all these environment this?
In which list? This one here?
Yeah.
All right, hang on. What I did is I said, we've decided that this is gonna be our major clay, and then we had a bunch of peaks still that we needed to figure out. So then I clicked search match again. And now it's a broad search match that's gonna go through all the mineral files and not just clays. And when I did that, I've chosen anorthite. Makes sense, right? Because that's your logic. You have a rock, you go by logic, you know, what's in it. And this is not, you know, a very usual thing, because what I knew about it is that it's a clay rock and it wasn't a clay rock. You know, that's kind of like, it was a complete unknown. All right, so now let's try and work with one peak. You can just create a box, just use your mouse, create a box over this peak at 20 degrees 2 theta, okay? Let go, and there you go. You zoomed in. Are we good?
Yeah.
All right. So now you can just hover. It's telling me what it is because I've looked at this a million times already. But in your case, it's probably not going to tell you to search for muscovite. So you can click on this peak and you're going to get a list. Did it work?
See the exception much remaining peaks kind of bottom is still there, so I mean. It wish me to.
I know.
Over-
It's yeah, so you have to, yeah, you gotta work with it because you have to be in this tab. But it's telling you something strange. Now I click differently. If you click, you know, like a little bit off,
I think what it is.
you can get, so it says Muscovite 2M1. All right, let's go with Muscovite 2M1. We can add that. And it's on my list here. I don't know, it put it like right there, so it's gonna be the fourth one on the list. Well, after you clicked. And I'm gonna drag and drop it here. So now this was labeled number 6, but it's not labeled anymore because we figured it out. Okay,
Can you show us how to zoom out? So I think my.
double click anywhere on the, like, don't click on the actual diffraction pattern, click on anywhere on the empty space and you can zoom out. It was on this list here on the side. Once you choose the peak, you click to search the peak, and then this list is going to give you, all right, okay, do you want to take a look at how I did that? I clear this list, so there's nothing here. I want to search this peak. I'm gonna click here where I think is the middle of the peak, and now my list has this, right? So I'm gonna say Muscovite and I'm gonna drag it over and double click here, zoom out. And now I can safely say that I'm missing a plagioclase or something like that. It makes sense, but we don't want to spend so much time here because we want to repeat this in a way in our database. So I just want to show you like really quick how you would do whole pattern fitting in JADE or a quantitative analysis. Okay, we know that we haven't figured everything out, but we can go to this little graph. It is where you have your, right next to your search match button. You click on it, you're gonna get another pop-up. So now this, has anyone ever done any kind of quantitative analysis like Rietveld or multi-phase? Okay, so this is that, and it's a very fast and effective. So I'm just gonna really quickly click some things. It doesn't matter what I'm clicking right now, because I just want to show you how this works. I'm not constraining like I should constrain the angles of anything that's triclinic and monoclinic. I don't want to change the angles because that can get into multi-phase analysis that can make everything very messy. So I should do that, but I'm not doing that right now. What I'm gonna do is I'm just gonna click refine. So I'm basically just refining scale factors, and in some cases lattice parameters. So it's giving me an error here, which I'm not going to fix right now. I know what this is, but I'm not gonna fix it right now. I just want to show you that JADE is very cool like this. It will tell you which phase has an erroneous value, and then you can go to it and fix it. So in this case, it's telling me that this phase basically doesn't exist. And that's because we have muscovite, which works much better here and is probably there instead of elite smectite. So if I got rid of it just by deleting it, and now I can do another refinement. And now I'm not getting an error, and my agreement is around 7%. Now this is not a good refinement. This is just a quick thing so I can show you how JADE works, okay? So it will tell you which phases you have percentage of them. You can go here and choose bar chart, and it will show you all the phases and their proportions, okay? So we can stop here, but just let me know if you have any questions right now.
Yeah, one that was like something that I face more. So say a couple of times I work with these cases of factor costs in the US. And when I tried to do a quantitative analysis, it became a whole mess because PDF database doesn't contain anything on lithium phase. So when I tried to make the
Lithium
phase, I mean the things that are there are probably a cesium heptaride, and that's about it.
Well,
so at the end, when I do, of course, the lithium refinement, you will get it because apart sometimes you have like these mixed layer clays as well. So I always end up with a RWD between 15 and 20%, but I guess it's just because the exact mineralogy is not there. As to for the process of the ritual to do the discrete mineralization.
okay, I'm going to say maybe, because I haven't looked at your data, but we'll be here the whole week, so you can stop by and talk to us. We'll be out like at the booth, and maybe we can take a look at that and then see what's going on, because off the top of my head, the answer is maybe.
Okay, I mean, I can just try this week with JADE.
Yes.
See how it goes.
Well, here's the thing. You're saying like lithium clays, right? I just showed you that you can have a clay that matches up with a clay that you have that's not necessarily the same chemistry. You know, so your chemistry doesn't necessarily control like your like diffraction pattern as much, you know, especially lithium, which is so light. But yeah, let's take a look. And yeah, try with JADE for sure. Now you've already imported the clay subfile into JADE, so you can work with that. And this is without me seeing your data, you know, I'm just guessing. Okay. If you're done, and we are done, I just want to show you this. You can save your data. We don't need to do that, or if you want to, you can just click yes, and JADE won't ask you where. You say okay, it will save it automatically to the folder where your raw data is. So then if I erase this and I go to a folder, I'm gonna go to Argentina Rock, and then I have, just showing me like edge files. Here's my work file, WRK. I double click on it. Oh no, stupid edge. All right, if I take this and drag and drop it, it will open the whole thing that I worked on last time, okay? So it remembers. Okay, so now let's do the same thing. They haven't looked at Civ, right? Yeah. Okay, so now let's do the same or similar thing in the database. Let's reset all here. And then there's this button up here. Are we all in the database already? Okay. There's this button here that says Civ Plus. You want to click that. And this is going to be our search match database analysis, okay? So we get this box here. Now I want to go and click import 1D diffraction pattern. Let's go back to bulk samples and let's go back to Argentina Rock. All right, so now we are not going to we're not gonna have it like JADE figure out everything for us. So we have to figure things out. So go to import 1D diffraction pattern, choose Argentina Rock, and then click open. So you're gonna get this box here. Now you need to set up your, make sure that you have the correct wavelength, and you're gonna have to process your data. So down here, you need to click new. You're gonna have to do this every time you import a sample in Civ, but you can, you'll get like really quick at working with it once you start. So I'm gonna say okay. And now I'm gonna get several options. One is to remove background. That's my first option. Civ doesn't work with the background. It will remove it and then work with everything that's above the background. So when you're working with clays, you have to pay attention to peaks at low 2 theta and tiny peaks, because you don't want to, remove them when you're removing the background, okay? All right, this is a really good scan. It's not noisy, so I'm gonna accept this background right now, but you guys can play with this. You can play with the grid size and repeats and see how, it's modeling the background, or you can use your mouse and like create a manual background. All right, so remove background. There it is. Now it's asking me if I want to smooth this. I don't. I'm going to skip K alpha 2. No, I don't have K alpha 2. I'm not going to strip that. Skip, and now it says find peaks. It found 35 peaks. I'm going to say there are a lot more than that. So let me lower the intensity limit. It's not helping. I think we're going to have to do this manually. I lowered you have options of intensity limit, the derivative limit. Now we have 41 peaks, which I think is still not enough. All right, well, as you're lowering this, you'll get more and more peaks. Some are going to repeat, but let's say let's put this at 0.6. And I'm gonna say accept 47 peaks. And then I know that I have this little guy here. I can zoom in the same way you zoomed in JADE, just like create a box around the peak. And then select it, okay? So now we've added a peak. Right click, undo zoom. And now you have that peak. Now let's see if we've missed like any major peaks like around here where everything is messy. like this one maybe. But I mean, in principle, we're good, but you get how this works, right? You have to make sure that all your peaks have been selected before you do your search match, okay?
I think. Find something.
Yes, if you want to remove a peak, just hover over the line, it like this line that you've chosen. And now your little hand is gonna have an X, and that's to remove it. So you just click and remove it. So here, if I added a peak here by mistake, now my hand has an X on it, I just removed it, okay? This box here is also to reset. You can just click it and reset the view. Are we all good here? I have like 53 peaks. You may have, 45 to like 50 something. Doesn't have to be the same number.
But you make, so if I see a blue line, that's a peak, when you press and right.
Yes. Are we good? Then we can click import. Now we get to this box that looks like our search box. Okay, or a search menu. And we want to scroll down to minerals, of course. We don't want to work with everything, so we want to click mineral related. And I want to click, are we good? I want to click apply filter. So what I'm doing right now is I'm applying a mineral related filter. Okay. All right, so there we are. Now we have a similar situation as we did in JADE. We just had to figure out the background on our own and make sure that we have all the peaks correctly selected, all right? So now the first phase is calcite, we know that, and we can see how nicely it matches here. If you're not sure, like just create a box around it and then see if this peak matches up, if like other major peaks match up, and they do, so you know that it is calcite. So in this case, we know this, and we're gonna go up here and say accept phase. Then the next phase is quartz. We know that, we're gonna say okay. So now things become more difficult, right? Now we know that we had the zeolite, which now I can't, well, we gotta find it. But we are not really seeing anything here. Well, we're seeing analyzing here, but you would have to scroll down all the way on the list to go to find it. Which is fine, we know that we have that right now, so I'm just gonna accept this phase. So now what we have now are clays, right? Clay related minerals and feldspars and pledge. Are we all good? Okay, so now I don't want to like go through this list anymore. All right. Well, we can actually, this is doing much better than JADE. So we have this illite smectite. I can say accept, before I say accept phase, I want to open the PDF card because I want to make sure that I'm not using like a glycolated sample or a hydrated sample, right? So I'm gonna go to comments and take a look, and it says same thing. You see, it's giving me the exact same result, heated to 823 Kelvin, meaning 500 Celsius. So it's the same one, and now, you know, we have confirmed for the second time, or this is, we've found it the second time, so we've confirmed that this is indeed the despacing that corresponds to what we have in our sample. So I'm gonna say accept phase here. And now, it's telling me that I may have another calcite, type of calcite, and it's telling me that I have anorthite, which I'm sure that I do. So I'm gonna say for anorthite, accept phase. So let's go back to our, see, this is our issue, same as before, because these peaks are extremely broad. So when we did this in JADE, we found that this is muscovite. So let's see if we're gonna get the same result here. Okay, so what do I want to do? I want to say set filter. So now instead of mineral related, I just wanna analyze clay. Okay, so now I selected clay here. It's giving me the same number, 356, right? And I'm gonna say apply filter. And what did I get? Nothing. Did you guys get anything? No? Okay. So what you wanna do, you wanna, let's call it like loosen up the search. Minimum goodness of match doesn't have to be 2000, it can be 1000. So here I already have something, a clay mineral rectorite. I can say you can exclude the second pass filter. These are all meant for crystalline substances, where these filters are going to remove false positives and are gonna lead to higher accuracy. But as I said, working with minerals, keep an open mind. You cannot expect higher accuracy or anything like that. You go with messy, right? Okay, so now we've unchecked that, and now we can change the search window to the highest that's here. That's like 0.182 theta, but you can also manually change it. So now I'm gonna do the match window, 0.18, okay? And now I have a lot more options. So we can try and match up this peak, but we're still not matching it up. So let's try and do a single peak search here in the database, okay? I zoomed in on our peak, and now it says that the peak is here. This has been determined by Civ. What I want to do is right click on the tick mark of the peak and say single peak search, okay? Single peak search is gonna give me, you know, how I'm gonna say 0.1. So I'm gonna search this whole, and this is too much. I'm gonna search this area. Well, not really area, but this length here, okay? And we have two things here, strong line and long line. This is very useful when it comes to clay minerals. Strong line refers to your highest, or sorry, your highest peak, despacing of your highest peak, tallest peak, right, of a phase. Long line is going to look at the first peak, first, second, third peak, okay? So you tell it, is it gonna focus on this as a long line or a strong line? I'm gonna go with strong line and see what happens, run search. Okay, well, this keeps telling me that this is rectorite. So I don't know. Who am I to argue now with it? You gotta say okay, because we don't have another option. So now this is something that, you know, you can, if you have JADE, you can go back and forth and make sure that you know that this is rectorite and not that kind of muscovite, and why that muscovite was similar to this rectorite. That's something that you would have to figure out when you're doing an analysis like this. Or you can do additional analysis to try and figure this out. So let's see, we have this peak. And then this one here, that can also be rector, right? So in this case, I'm gonna say, okay. And I'm gonna say accept this phase. And now it has no more options for me. So this is how you do your search match of a multi-phase natural sample in our database, okay?
It's this goodness match.
Mhm.
How is that calculated? Do I know what that really means?
That is comparing your, how many, 9 or 8 peaks, Tom? Hey, Tom,
Yeah,
how is the goodness of match calculated? It compares like nine tallest peaks of a phase, right?
there's a match to take with 8.
8.
A perfect match being position and intensity, it's a score of 1,000. So your 8,000 would be, you had it perfect.
So perfect overlap, it's like 10,000.
So perfect means that the peak position that you get, the peak position reported in the PDF entry are identical. Now, what begins to happen is you could have a little sample displacement. PDF entry could have had a little sample displacement, so there's always the potential for a little variability. Now, what can happen is, let's say you happen to be looking at a limited data rate, didn't run out the 78, 90 degrees, you ran out of 50, when we had 3 peaks. And then the problem is, you might have 3 peaks perfectly, but you don't have 5 peaks in your pattern that are in the reference to your goodness of match will drop, just because you didn't match 8 peaks. But the general guideline is that a perfect score is 8,000, and then it goes down lower depending upon, primarily it's the peak position, secondary is intensity. So in the box up there, throughout the middle where it's weight, the D spacing, if you're giving extra weight to the peak positions, a little less to the intensity. Sometimes you will do that. I think you have a little curve orientation. So.
Okay, go ahead.
Can you show us?
Yes.
Yeah, and if you don't mind, like the moment that you switch it from minerals to clay, like I lost that.
Okay.
Like,
All right, I'm gonna review the last phase, which we said was rector, right? So, all right, first the single peak search. We were searching for this one here. You want to like just create a box around the peak. And then you see this tick mark, it's very small. This is the tick mark that Civ determined that this is the D spacing for this peak, okay? You wanna right click on it and then go to single peak search. You click single peak search and then you get this box. So now in this search window, you can give it more or, you know, less freedom to search for the peak. So, you know, this wouldn't work. So what we want to do is find something that's going to be sort of broad enough, like this peak, in case that, you know, the peak, the phase is going to be here or here. So I've chosen 0.05. Okay. And then I ran the search and I got the rectorite. And then to constrain the search, you can go to set filter. So you can click on set filter, and then I've chosen clay. and set apply filter. Our first filter was mineral related, same thing as we did in JADE. So when I did mineral related, I searched all the minerals in the database. Then I switched to clay and I searched only these 356 entries. Okay? Any more questions?
I have like a WB papers.
Okay, so you need to, you need to give it more freedom, so you wanna change the minimum goodness of match from the higher value that you had to like about 1,000. You can make the search window and match window bigger to 0.18. Remove the second pass filter. So you're just like removing constraints, giving it more freedom to search. If you have a very difficult phase, you can manually increase the search and match window, and you can do the same thing when you're doing your single peak search. But I mean, that already has, you know, enough of like freedom to search for something. Okay, is that break time?
So,
Okay,
about 10 more minutes, they said.
okay. Any more questions? Okay, I think this break is coming at a good time because I see your faces and all I can say, I'm sorry. But yeah, this is your, I don't know, like, what should we call it? This should be your, like, your train of thought. You go from the most obvious to the least obvious, but you have to consider what you may have and like how difficult your sample is, how different your phases might be, and then try and give it as much, you know, you should be as specific as you can, but at the same time, give it enough freedom to search for, you know, for all the possible minerals that you may have in your sample. Okay?
Will you, for example, the compromise in between these last piece, for example, the one that you were looking at, because you choose the 70-30 record.
Elite
choose that one. You won't ever find that 20 because that's a 0-to-0 reflection of the phase. It won't ever pop up in a random orientation. That's not for it slide. So, like, how do you do the combination of the
Because clays are never random. To create a randomly oriented clay is a lot of work. It's very difficult.
Yeah, well, what I mean is powder that is not in a sedimental slide. That's what I mean by random.
Well, your clays are not going to be random in that powder. So it's totally like, okay, I think we're all right. Let me see.
Yeah, just forget that I say random. Yeah, random doesn't exist. What I mean is the 70-30 rectorite, you're
Elite
placing as a
smectite.
pattern.
70-30 was elite smectite.
Yeah, well, the one that you're highlighting, for example, is one.
Okay, so that's rectorite.
Okay, so if you choose this one, like, you will always avoid the 20 because the only way that you could came to the conclusion that that's a rectorite. I mean, I guess if you open that as a PDF card, you will see that it's an oriented slide.
Okay. So let's go to comments. What do we have here? We have the chemical analysis, alternating illite and morronite layers, so that is fine. We don't air dried, 50% relative humidity. Okay, so this I'm gonna assume is an oriented slide. It doesn't say specifically. But what is your question?
So if you separated, you will already identify that you have some gates and you can go more in depth.
Yeah,
Like the thing that you should do then is take your sedimented slides and try to compare as you show us at the very beginning of the session.
okay, yes, that is, we're looking at the bulk sample now. Yes, if you're looking at your oriented slides, that's like after you do sedimentation and you create less than 2 microfractions and you do oriented slides, that's a different story. Then you have then it's gonna be pretty, like, it's gonna be more straightforward. But in many cases, you have to get some kind of, or many people, right, have to get an accurate phase ID of a bulk sample, including clays. And many people who come to ICDD have to do a quantitative analysis with clays. So this is what we were doing, you know. So
Bulk samples, yeah,
sorry.
you can do detailed clay quantitative analysis for a bulk scan.
Well, that's what we did in JADE. And here you have an estimate in the PDF as well, based on reference and density ratios. So let me show you something. You can, let's add this rectorate. And then, all right, I don't have to click complete phases because we have all of our phases. So we want to zoom in here because these are our peaks that are very broad and very strange. So this is going to be a rectorite. What you can do, what Tom was showing, you can change your, in this case, let's start with chrysalid size. So now the chrysalid size is very broad. We don't want it like that small, but here it is. If we go to 100 angstroms, we've more or less gotten this correct. So now that I'm looking at this peak, there may be something else here, not just rectorite, but this is fine. This is perfect. So what this tells you is that you do have a clay mineral in there, and it is pretty pronounced, but it's a very small crystalline size, which is very common. So you have these broad peaks. You can use the database and play with it with the crystalline size and try to figure out if that's your, that's really something that you have, and if it matches the pattern, fraction pattern, okay? All right, any more questions? Okay, so we're gonna go back to JADE and I'm gonna show you some of the features we were talking about. Okay, so we're back at our, JADE will open the latest file that we worked on. So we're back at our Argentina rock. So here, this is where I was saying this cursor clay despacings. This is a despacing that were taken from Brindley and Brown. So if I'm gonna zoom in here so it's easier for everyone to see, and I try and match this peak, what I can see. All right, let me get rid of everything because there's too much going on. Okay, so I'm gonna choose this. So these 3 parallel lines, that's the clay D cursor, and I'm gonna hover over this peak. So it's gonna tell me the first thing, smectite in various hydration states. That is gonna be your, a given, let's say, because you see what the range is. It ranges between 9.6 in this case, so 10 to 19 angstroms. So the range is huge. So any, clay peak is gonna show you that range. First thing is gonna pop up, is gonna say smectite in various hydration states. But at least that that is most likely, clay or clay related. So then this list is not giving you minerals in their, like, in their order of probability. It's just giving you a list. So you can go down this list and see all the possibilities that you may have in your sample. So now we're at like more or less 10 angstroms. We said this is muscovite or rhyolite smectite. So, we see that, right? We see muscovite. We see smectite collapsed. We see all of these possibilities. So if we go to like a higher 2 theta angle,
See big stuff on the screen.
do you see this on the side?
Yes, and then that's it.
So you just position the cursor on your peak.
I actually don't have the option of like the three levels. We were just lost in there, so many buttons, nothing else to. This one you're looking here. Type it.
Okay, so you have a different menu. Click on scans here.
Here.
No, here, this tab scans. I wonder where this menu is. Is everyone missing this? The clay one? Where is it on in your Jade? Same?
Yes, imagine.
Okay. No, it's one of the floating menus. Okay, see if you have.
So you know, like this one, but this way. So it's
It's not it, it's
Let's see if this actually.
okay, let's figure that out
Yeah, sure.
later. That that menu for you is hidden. That's the problem, cause it's there, but I don't know exactly why it's hidden.
Explain these spacing is the name of the command.
Yes, did you find it?
Well, I find it through cursor.
Okay, good.
Tab,
Okay,
cursor.
yeah, so you can go, okay. From the cursor menu. And then you got the clay D spacings. Okay, so you're missing this menu. I don't know why.
Yeah, that's.
Okay, so we were talking about this peak, and then if you have a peak at, this is like 12-ish angstroms, 12.5. It's not gonna give you such a long list, because these are gonna be clays with higher D spacing, with larger D spacing, so it's telling you that this is smectite in various hydration states, so you know that this is most likely smectite. Okay, and then if we go to 7. 7-ish, here we are, it's gonna start giving you, here's the kaolinite, it's telling you, well, now we don't have an option of smectites anymore, because this is gonna be a non-expandable clay, so it's gonna give you a list of different clays that this is, this would be the basal, peak, okay?
Can you change for this one actually like the interval or it's just by default?
No, this is a list, if you remember, seems like a long time ago. I showed
Just to make it my-
yeah, too much, I know. Let me see, where is it?
One of the 80s.
Yeah,
Yeah, okay. Now
hang
get
on.
back.
here. So this is what I showed you earlier. This is the list. This is what the list looks like. So if you like get your hands on this book, or if you have it in your lab or something, if you take a look in the middle of the book, there's a long list, like I don't know how many pages, of all major peaks for major clays. So this is what it is. This is what it looks like. It says kaolinite around 7.2, and it says non-expandable clay stable D spacing. And it goes like that. It's telling you, it gives you some info, like what we saw smectites in various hydration states, and it's telling you what the basal spacing is, okay? So that's what it is. That's why you can't change it. It just it's something that helps you, you know, understand if that's a clay or not clay and which clay it could be. Okay? All right, so should we, it's 3, I guess, we should do, like, take a break. I don't know, like, clear your heads. And then we'll go back to Jade after the break. And okay, so we're back. We're gonna try and not go into like too much as we did in the first part. I see most of you have fairly complex questions, so we'll be here. We have our booth like right there in the corner next to the Mineralogical Society. So stop by and we'll help you and answer your questions. So what I want to tell you is that we have just like scratched the surface with Jade and what Jade can do. So I'm going to show you right now a little more, not necessarily advanced, but clay clay focused toolkits. Okay. So I can go back to the truck. Okay. So we did this kind of analysis. We figured out what's in our rock. So now we can talk a little bit about the clay toolkits. So what are the 2 major clay toolkits that we have in Jade is the pattern matching toolkits and oriented clays. So for you guys, I mean, both could be very interesting. Pattern matching toolkits, is matching the whole pattern. It is not doing a retooled analysis. It is matching your pattern to a known library that is in Jade itself or in the toolkit. And then oriented clays works in a similar way. It has a library embedded in there, but you're working with oriented samples. You can model single phase clay. You can model interstratified clay, and you can perform some kind of quantitative analysis. So for those of you who are asking about the quantitative analysis of oriented clays, that might be the answer. That's all in Jade. So we're gonna do this very quickly. I don't think that I'll be able to show you all the features that we have in these toolkits, but I'll just do a quick, overview. So as I said, full pattern matching is inspired by RockJock. Do you guys know what that is, that program? Okay, so it contains the RockJock libraries and then some additional patterns. What it does is it compares the library data with your pattern. So it scales the intensities. What can happen is that you miss a phase simply because there is no a standard, let's call it, or a phase in the database in the library that you can compare your phase to. For this, you should follow a certain analysis, 5 to 65 with a step size of 0.02, which is fairly common, so it's not necessarily a difficult thing. That's sort of how we normally analyze our data. So I'm just going to show you this in a bit. You get like these nice analysis that you can, just click through and see what your ratio of phases is. So you'll get a quantitative results. And this is, you'll see once we go through an example, you'll get like which phases were chosen for you, what is the number of the standard, how much it has been shifted, and that is what's going to do. It's going to implement a unique shift for each standard. So it's going to shift each one to fit your pattern. Okay. All right, so let's go back to our clay. I'm going to show you the healing clay because that is a sample that's been, it's a demo sample, so it works really well. Okay, so your toolkits can be found either start and then go to MDI toolkit and call it from here, oriented clays or pattern matching. Or you can go down here to these tools right here, click on that, and you can choose the toolkit from here. Other toolkits are also very cool. You can digitize XRD diffraction patterns if you need to. We end up needing to at work, so this is super useful. You can do morphology, charge flipper. There's a Raman toolkit in here, and they're constantly being developed. So, okay, now we're going to pattern matching toolkit.
Also don't have an ace option. There's some here like break with back.
From the, you don't have it if you go to start menu and go to MDI toolkit.
I know. There are many options that I don't have, like they are actually in break.
What about the rest of you? Well, I mean, to be honest with you, that's okay for now because we have to do this really quickly. We have basically just half an hour left. I asked Stefan, he said that they have everything.
Yeah, well, I was trying opening the part on this.
We'll see if they can do an update. Okay,
What else do we know, make sure that updated there? That all the features will be.
yeah. Okay, so let's go back to our Argentina sample. Okay, so we know the sample already. What we have here, we have three options. We have, we can work with two internal standards, corundum or zincite. Zincite was the standard for the original rock jock, I guess after they added corundum as well. Or you can choose none, because this was meant to be used with internal standards, but this toolkit was made so that you don't have to. So this has been normalized so that you don't have to use your internal standard. If you click here on manual shift, you will automatically get a peak for quartz, zincite, and corundum. So you can go to, you can zoom on to your quartz peak, because I don't have zincite or corundum, and just use my mouse wheel to scroll and set it up. So this -4, I mean, I don't know what, this is not like 4 degrees to theta or anything. It's just how this is calculated. So we have here fit individual shifts, which is what we want to do for each phase. Fit level background, it's going to fit the background and normalize to 100%. You want to do this when you don't have an internal standard. So you want to keep this option. Then our next step is libraries. You have 3 different libraries. And if you're using an internal standard, zincite or corundum, that's the library you want to check. I'm not, so I'm going to go with the normalized library. Now I have this list of minerals. What is in black letters? So blue is the internal standard. If there is corundum in your sample, you of course don't want to use corundum as an internal standard, or same with zincite. So you can choose that as a phase that's in your sample. What is in black are minerals, in reddish are clay related minerals. So a very cool thing here is this rank histogram. Rank histogram is something that will give you a similarity index. So if I click on it on the tallest bar, it is automatically going to select all possible phases. So you can choose as many phases as you want, because this is really quick and it just compares the peak heights. So I can go back to this tab, the FPM tab, and click start refinement. So when I'm clicking start refinement, I'm not refining structural parameters. I'm just refining the ratio of these phases. So we have 130 phases selected. I'm gonna say start refinement. And if you take a look down here, it's going and it's very quick. So it gave me a bunch of stuff. And now we know already what's in our sample. So we can, once you click on the phase, you can see what the original diffraction pattern is. So you'll see a bunch of diffraction patterns that have these lines, like just straight lines. And that's because when this was created, these were samples that had impurities. So impurities were just removed. So you end up with these lines where the impurity peaks were removed. So why do we have ferrihydrite here? Because it describes our background very well. And it has this amorphous hump, which we don't really have in our sample. So we don't want this ferrihydrite. So I'm going to click delete. And it will not delete it. I'm going to remove the phase. Okay, so now I don't have this ferrihydrite. So you can go through the list and remove everything that doesn't make any sense. And then let's see this marcasite. I'm gonna say no. And hydrite, maybe that's what it always wants to find. Then barite, definitely no. And then just pure iron, no. So once I remove all of these phases, I can refine this again. And I'm gonna get a different fit. Okay, so how is this useful? This is super useful if you have similar samples. First of all, you can do a batch analysis. I'll show you this in a minute. You can do a batch analysis of a bunch of different samples at once. And the ones that we have here, the analysis is done in a couple of, not even a minute, in like, I don't know, 15 seconds. And that can be a really good starting point for anything else that you want to do. So if you're working with the same, like with soil samples or samples from, that generally have similar compositions, you want to use this, you may want to use this because it's going to give you a really good starting point into what you have and where you can, go from there. So if you take a look here, this is what I was telling you. It will tell you, what it thinks you have in your sample and how much of it. This is going to be your result. You can click here and then go to print preview and have like a really nice printout for you to use as a reference. Okay, so let me show you quickly batch processing. If we do this, and then I go to, this is corundum as an internal standard, then I can go here and change the library and choose corundum. So I can click on my histogram. It's going to choose a bunch of different phases, 133, and I can click start refinement. So I'm not really counting, but it's already done. And it analyzed these 8 phases. It's giving you this chart that's showing the composition. So like each color represents a different mineral and it's color coded, so you can see which mineral that is. And then we said that the corundum is the internal standard and it zeroes it out. So it tells you, it sums everything up to 100%. So now we can stack the results. I go click and show overlays. I can see all of my patterns and analysis, and then I can click on stack, or I want to pull it out. Let me see. I don't want to see this embedded. Oh, okay. Well, I don't know if I can show you this right now. All right, well, you can see the stack results like this. There is a way to pull it out, and like it will be like a floating 3D graph, which is very cool, but I can't get it to do that at the moment. So these are sort of your results. Okay, so this is the batch processing. You can take a look at the film view where everything is. And then go back to your standard list. Okay, so any questions here? All right. Okay, so let's go to our next toolkit. So this is the oriented clay toolkit. And this toolkit has many features. So we're really running out of time here, but let me so some things that you can do. You can look at oriented clays, of course, it's called the Oriented Clay Toolkit. You can model these clays by changing different parameters. This is also inspired by NewMod, not also, this is inspired by NewMod, and it has the phases that were used in NewMod, and then some additional phases as well in the library. What this says defaults from Reynolds book, that's what's in the clays X-ray diffraction and clay minerals book, and the NewMod program. You can add your instrumental parameters. So this is kind of what it looks like. You can model clays by changing the D-spacings, by changing the amount of cations. You can change the N1 and N2, the number of unit cells, proportions of phases, and our Reichweite ordering. Okay, so I have a bunch of slides talking about the probabilities of phases and ordering in interstratified clays. So just let me know how familiar or unfamiliar are you with these things? Yes? No? Okay. All right, so clays are layered structures. So we have a Reichweite ordering, which refers to the range of the atomic interactions in interlayered clay. So how much one layer is influenced by the next or is influencing the next. So that Reichweite means range. So like how far this layer is reaching to influence next, or the first, the second, or the third layer. Okay, so we have R0, 1, 2, and 3 in the oriented clays toolkit. So if we have clays that are randomly stacked, there's going to be no ordering. This ordering is going to be completely random. So the R is going to be 0. When R is 1, we have the type of layer that we have is influencing the next layer. If R is 2, one type of layer is influencing the next 2 layers. So this ordering is influencing the position and the shape of basal reflections. This is important for oriented clays. So in random ordering, we have more like broad and diffused peaks. Nearest neighbor, we have some sharpening. second neighbor, more structured pattern, and if we have R3, that's the long range ordering, and that is that's that's a structure that acts more like a single phase clay. So this is an illite smectite sequence as we are as the amount of illite is increasing, the ordering has to increase as well, because you're having less and less smectite layers, so you have an R value that's going up towards 3 as the amount of illite is increasing. So if we were looking at 70-30, so that is this, where R can be 1 or 2, and we're gonna look at this example right now, illite smectite 70-30. Okay, so this example. All right, let's not since we're more or less out of time. This is saying that if you have a 50-50 mixture, you can have a more or less alternating sequence of layers, so you'll get a more regular stacking. If you have mixtures that have more than 80 or 90% of one type of clay, like illite, you're gonna have a more of an ordered stacking. Okay, so where is this important? Mostly in petroleum geology, but also once you have your clays, you may, and you want to model them, you want to keep this in mind, even though you're not working with petroleum geology. This is important in illite smectite transformation sequences, because you want to figure out how much smectite has converted to illite, and then relate that to carbohydrate production, okay? All right, so let's start looking at the oriented clays. We can look at the single pattern simulation, the series simulation. We can look at the pattern mixer, phase matching, and genetic algorithm. I'm not going to show you the genetic algorithm. I'm just going to show you the results and the setup for it. So, all right, these are just examples of single clays and mixed layer clays. I'm going to show you this in a minute, and how you can you can do these models. Then we can move on to pattern series, and I can show you how one of these parameters can influence the diffraction pattern. So we were talking about R ordering or the proportions. So you have an option of modeling a series of diffraction patterns with different ordering or different proportions of of two clays. And then pattern mixer and phase matching in genetic algorithm are more or less quantitative analysis. Well, they're quantitative analysis. Genetic algorithm is inspired by how genetics works, how you have like random mutations and changes in chromosomes. So that's kind of what it's using as a path for calculations. It's a brute force calculation. So none of these methods are doing a structural refinement. They're just doing matching and calculating the weight percentages. So this is what it looks like, so that it resembles chromosomes. This would be like one chromosomes there with 21 parameters. So you have these 21 parameters that are chromosomes, and as it's calculating, these are just gonna change, you know, and it's set to do 100 cycles of calculations. But if you get solid blocks, you know, green, blue, red, it converged and it got to its final value. Okay, so what we have here, all right, let's go to oriented clays. All right, so this is the oriented clays toolkit. My pattern is this purple reddish one. And then the pattern that we have is just, we have two patterns of kaolinite. This is the one that's in that's this one. Okay. So we have an option of auto scaling everything. So this will, things will get blown like way out of like scale. So you want to go back to this button and click auto scale. Here we have our chemistry for the clay that we've selected here. And if we click this here, now I'm showing two kaolinites. Let me choose a different clay, an alite. Now I can see an alite and kaolinite, and is you're changing the structure here. So let's say that this alite is going to be 10 angstrom. You can see, take a look here, how this layer thickness is changing. So as I'm changing this value, the layer thickness is changing, and also is the simulated diffraction pattern. So how am I'm just mouse scrolling. Anything here, you can like mouse scroll, and things are gonna change. The values are gonna change. All right, let me just rescale this again. Down here, we are working with copper. So this is gonna be copper. You can change your starting angle and ending angle. So I'm just gonna do 35 here. And I don't need to start at 3, I can start around 4. So that's fine. You can just scroll. Step size is 0.02. So you can set this up with your instrumental parameters, and then you can right click and say save as, and then you can save, you can just give it a name and save your instrumental parameters. So you can, if you're working with several different wavelengths, you can save several different instrumental parameters and wavelengths, and then call it up when you're working with these patterns. And you have to do this because if you have wrong wavelength, everything is going to be wrong. So we said my major clay is going to be dimica or illite, and then secondary clay is going to be not glycolated but with water, dismectite. Okay, so now this is what I'm saying, totally blown out of proportion, and here it is. So now, okay, we're matching up this really well. So now how you want to model your pattern. We said that we have 70% illite. P1 is the proportion of major clay. So if we have P1 0.5, that is a 50-50 mixture. We know that this is 0.7, so we can go up to 0.7. So now we've changed this to 0.7. So let's just rescale it, and there it is. So now, do we have ordering 0? We don't, because it's not random. Do we want to up this? And now if you go like scrolling, it's going to tell you what is not possible, because you can have R ordering more than 2 in this case, because you're limited by the proportion of the two phases. If you have 80 or 90% illite, then your R can be higher than 2. Okay. Okay, so we can assume that R is 1 here, and then go with that. Then you can change the D spacing here and see if it works better. You can up the smectite D spacing. You can change the amount of cations, which is going to change your peak heights and so on. So this is how you would model your clays. It's not a super straightforward process. You should know what you have, but you have a good library here that you can work with. So let's go to phase matching. Now we're gonna get into a little bit of a quantitative analysis. If I go to phase matching, I'm gonna get this list that's gonna tell me that I can search all of these different clays. So I know that this is gonna be an halite smectite, so I'm gonna stick with this. And I'm gonna say run. Okay, so here are my results. I'm getting a bunch of different results. Dimica, dismectite, 2 waters. Okay, I'm gonna say, okay, we tried modeling with 1 water. So if we had time, we could have switched the modeling to dimica and dismectite with 2 waters and our model would have been better. Okay, all right, so I'm gonna say this, but then I have this one peak here. And I know that this peak is kaolinite because it exists as, let's call it an impurity. Clays are never pure. It's rarely, it's kind of impossible for you to have like a very pure clay. And these are Clay Mineral Society standards. So this is basically as pure as it gets. And I mean, there is a kaolinite peak, so what can you do? Okay, so now I can right click here. We're gonna go to tools, phase matching, remove unchecked. So now I have 2 phases here. So now we can go to create a mixture set. So once I do that, it's giving me a pattern mixture and it's telling me that my major clay, which I know, but I mean, if you didn't know, it's telling me that my major clay is the dimica, is the halite smectite, and it's telling me that there is kaolinite. It's just creating this broad peak here for kaolinite. So this is an estimate. What I know from this is what my major clay is and what the minor clay is. If I had chosen a bunch of different clays from the list, it would tell me 0. So I would know to remove them from the list. Okay, so what I want to do now is create a genetic algorithm set. So here's my genetic algorithm. It is telling me that it's going to look at P1 0.5. Kaolinite's not giving me anything. So what I can do is click here on weight percent, and it's telling me 0 to 1. So everything again is clickable. So you can change and modify all the parameters here. So now you're doing a more like in-depth analysis. Now I know that my major phase is major. So I can say, all right, I'm sure that I have more than 50% of it. So I don't need to count from 0, I can do 0.5 to 1. So it means that it's going to have, there's going to be at least 50%. That means the kaolinite is going to be 0 to 50. It cannot be more than 50. So it does that automatically for you. So this is the number of unit cells. And now if I up this and I say more unit cells, there's possibly more unit cells of kaolinite. What this helps me with is it helps me with crystallinity. So it will calculate kaolinite and it will be able to simulate the sharp peak. Because if I leave it as low and 2, it won't be able to create a sharp peak for kaolinite. It will think that the peak is going to be very broad, as it's showing right now. So once I do all this, I can go to tools and then genetic algorithm and then go to setup. And this is what we were saying. This is based on genetics itself. We have the size of the population, which is 100, which means that it's going to do 100 cycles. And within these 100 cycles, it's going to go through reproduction, crossover, and then every once in a while, it's going to introduce a mutation. So it's randomly going to change your parameter. It's a little abstract, I know. So it's randomly going to change a parameter, and that's going to help the calculation maybe go in a different direction and have more options, right? That's something that in genetics is called having like a healthier, a better offspring or something like that. So I want to up the mutation rate. I want to click here, and again, everything is clickable, and I'm just going to up it because, oh, sorry, wrong keyboard. Because that's how the calculation is going to go quicker. So we're in a fairly slow internet here, and this is not, this takes a while. So, all right, I'm going to go here and say genetic algorithm run. So it starts with random. It says here random. I don't know if you can see. It's giving a complete random distribution of parameters, or like quote unquote chromosomes. And now as it starts going, you can see here that it's going through trials, and it went through 100 trials. Once it did that, it said, all right, I did my trials, I have my starting point, I'm gonna start the calculation. And now we have already the second generation, and it's going through these steps. It still has this random thing. It's gonna change colors in a bit in like green, red, and blue, which is reproduction, crossover, and mutation. Okay. So I was gonna fairly like see it changed colors already. So this is what it's gonna look like from now on. And you will see as it's going through these sets of calculations, it's going to fill in some of these, let's call them blanks. And it's gonna try to get to like the converging point. What it means converge is when you see this calculation, well, plateaus, it levels out, meaning it's not creating anymore it's not creating new offspring anymore. I'm calling it offspring even though it's very confusing. It's not creating, new parameters anymore. It's happy where it is, and it can see how you could do more than that, so that's the end. Or you go to like 100 cycles. Okay, so I'm gonna stop this. Interrupt, yes. And let me show you, where's my PowerPoint here? Okay, are we on full screen? No, you're seeing this screen, sorry. All right, if it. Okay, all right, whatever, I'm just gonna stick with this. Okay. So. Okay, so this is the genetic algorithm. As I said, this is a good thing to point out. So genetic algorithm is what's called brute force. There are no refinable parameters. It's not refining anything. It is just using all your input and doing all of these different combinations in its calculation of different phases. Okay. So there are challenges with multiple phases of the same mineral group. It has a very hard time calculating that. And it's very sensitive to experimental set of parameters, but it's a very good tool for you to have an estimate of the clays in your sample. So this is what I was saying. How do you know, like after 32 generations, there's no change? Actually, we were at the 70 trial, 72 out of 43. No change for 32 generations. So this is what's telling me for 32 generation, there's no change. This line is flat, nothing is changing. So then if you see that, you can stop the genetic algorithm. So here you can see that kaolinite has been included. The pattern has been modeled fairly well. And this is what we're having here. 98% elite smectite, 2% kaolinite. And now this here is a calculation where I did not up the N2. So it came up with only 2%. Now I went and I did the same thing with the glycolated sample because I want to show you that you can do that with the glycolated sample as well. We haven't really talked about glycolation, but you know that when you glycolate a clay sample, all expandable clay is going to expand like this, and the non-expandable clay is just gonna stay, it's not gonna expand. So what's gonna happen, you're gonna see a split of the peak. So this is the same exact sample that we just looked at that had one peak. Now it has two peaks because the expandable clays are here and the non-expandable are here. This was the interstratified clay. Now kaolinite is still there. So what I did here is I upped the N2 and it came up with close to 6%. Okay, also, I mean, to be perfectly honest, this is not physically the same sample. So, you know, they're two physically different samples, so maybe one of them had a little more kaolinite than the other, but, you know, you don't know. Okay. And lucky you, we're done. I mean, we can talk about a lot of stuff here more. I didn't show you the one parameter changes in the clay toolkit. I don't know if that's something that interests you right now. I can do like a quick run through. If not, you can stop by our booth. Tom's saying, oh, you can. So, okay, anything that you need, I know that you had questions. I said this already, just stop by the booth. We'll be here. We'll talk to you about your samples and whatever you know you want to know. All right. Okay, so thanks everyone who was online.